Wow, wow, wow. It's coming. I'm excited. I hope you're excited. Here's the beginning of AI Day. Not the beginning of AI Day, but this is a cool part of AI Day. This is the fun part everybody wants to see. Just to warm you up. Come on, you were dancing. Admit it, you were dancing. Were you excited? Were you ready? So, TeslaBot is actually not the most important thing from AI Day, but we're going to talk about TeslaBot first, and then we're going to get into a lot more. So, there's a lot going on. I don't even know what I'm doing here. There's a lot going on at AI Day. And I've got a ton of clips from AI Day. I'm going to go over different bits and pieces of what happened on AI Day. I figured I'd start with TeslaBot because I think that's what most people are interested in. I think the most important part is Dojo. This is going to be a marathon session. I have tons of clips, tons of different things to talk about. So this is going to be a little bit crazy. And I do thank you. I do want to thank the Vasa Law Firm in Sweden and all my, let's get that up here. I do want to thank the Vasa Law Firm Sweden and all my Patreon supporters for helping this channel grow. But let's get to it. Listen to Elon.
Unlike Dojo, obviously that was not real. So Dojo is real. The TeslaBot will be real. But basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are like semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all of the neural nets recognizing the world, understanding how to navigate through the world, it kind of makes sense to put that onto a humanoid form.
This is a critical detail here that basically what happened is Tesla has developed all this technology that enables robots on wheels. The cars, self-driving cars, are robots on wheels. And as long as you've enabled all the technology for robots on wheels, putting robots on feet, humanoid robots, is a relatively trivial challenge compared to getting the robots on wheels to work and really perceiving the world. But let's keep going. Sorry.
We're also quite good at sensors and batteries and actuators. So we think we'll probably have a prototype sometime next year that basically looks like this.
So this is the introduction to TeslaBot. I think that this is the thing that the mainstream media will pick up on, the general public will pick up on. Tesla is planning to build a humanoid robot. Now, this was not that big of a surprise. If you watch this channel, I interviewed James Dauma, and James Dauma's prediction was, and I hopefully will be interviewing James Dauma again in a few days. James Dauma his prediction was a generalized humanoid robot. I talked about a roofing robot. I still think, based on what we heard in the presentation, that a roofing robot is a likely use of the Tesla humanoid robot. But, how do you take this technology they developed, particularly the real-world AI and machinery that can operate in the real world, how do you take that and make that most useful? And as James Dauma put it, well, we operate in humanoid space. Humans operate in humanoid space. So if we operate in humanoid space, then a robot that operates in humanoid space is probably the best choice for how to, use this. 1 second, please. My dog wants to come in. My dog loves the live stream, so she's on the floor over here. What? She's got to get in on it. I'm sorry. Okay, so let's move on to next.
And it's intended to be friendly, of course, and navigate through a world built for humans and eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it. And most likely overpower it.
really interesting here that Elon is making an effort to distinguish, to address the fears that people are going to have about TeslaBot being some sort of Terminator. Like, this is what, I mean, we're all joking about it, but the practical reality is if you make it small and you make it weak and you make it slow, then it's less threatening to humans. And it's designed, if you look at the design, this is not like big shoulders, forward shoulders, tall. It's 5'8". It's not 6'4". It weighs 125 pounds. It doesn't weigh 250 pounds. It's designed to not to look aggressive, and it's functionally designed to not to be capable of aggression from a AI perspective, but also just from the strength that they expect the robot to have. It will not, you'll be able to overpower it. You'll be able to outrun of it. This robot will not be dangerous to you. But there's more here. What is it? What else does he say here? I'm sorry. First time I've done it this way.
So hopefully that doesn't ever happen, but you never know. So it'll be a light, yeah, anyway, 5 miles an hour. If you can run faster than that, you'll be fine. And it's intended.
So again, you can run away from it. It's not a threat. You got some technical details here. I'm sorry. I've never done a live stream like this before, so I'm trying to work with what I got. So we got some technical details of the TeslaBot here. 5'8", 125 pounds. There's a screen on the face for useful information. I believe this is a screen on the face for us to get useful information from the robot rather than the robot is getting useful information from its screen. They've got plans to use lightweight materials, human level hands. I'm not sure where that comes from. 2 access feet for balance. They've definitely been working with, or I know we've seen the Boston Dynamics Dogbot. We've seen that on SpaceX property. I've seen Liv Boeree and Grimes playing with the Dogbot. I don't know where Tesla's finding its robotics engineers from, but it appears that they have hired or are hiring robotics engineers. I think I saw there was a job posting for it. And you can see the reference to 40 mechanical actuators, 40 electromechanical actuators, 12 in the arms, 2 in the neck, 2 in the torsos, 12 in the hands. That is a very dexterous set of hands if you've got 12 mechanical actuators in the hands. One of the goals here is to have very useful hands, which is what makes humans particularly useful, right? The opposable thumb is something that makes us, something that supposedly makes us distinct from a lot of animals. 12 actuators in the legs. This is a very complex machine, but an important detail for me is at 125 pounds, this is going to come up later. If this machine weighs 125 pounds, it has 40 electromechanical actuators. We're going to see more about this. I want to cover that more in a minute.
This, I think, will be quite profound, because if you say, like, what is the economy? It is, at the foundation, it is labor. So what happens when there is, no shortage of labor? This is why I think long-term that there will need to be universal basic income.
So for those who follow me closely, I'm not a fan of the universal basic income concept. I'll briefly disagree with Elon here. I would love to talk to him about it sometime. I understand that we face potentially a world of a large number of robots that will be, and I'm going to talk about a large number of robots later. That a large number of robots will replace a large amount of human labor in the routine, boring, repetitive, and dangerous tasks that we do at the beginning. And over time, it will be able to do somewhat more complex, and over time, more complex, less repetitive, more challenging work. But particularly, these robots are designed for physical labor. If you are doing non-physical labor, then this is certainly less of a threat to your job. And the hope is that this will make it so that you will be freed up to do something else. And this is I'm sorry to jump in on Elon here, and I would love to talk to Elon about this. There is a principle in economics. It's called the law of comparative advantage. You have a nation like the United States that is really good at everything, and you have a nation like Somalia that's really not good at anything. And the idea would be, well, why would the people in Somalia work at all when they can't be as productive as the workers in America? And the answer to that is, if you look at economic models of the law of comparative advantage, that You find what you are best at relative to the other country or the robot, and humans end up working in the area where they are most productive in a relative sense. And that would, I would think, in particularly be creative occupations, occupations where there's more interesting work to do. So really what this enables is, if the robots are making all the basic stuff we need and they're doing all the basic tasks that we don't really want to do, then we as humanity are freed up to do more creative work, more interesting work. Rather than thinking as we're unable to find work, this frees us up to be able to do more. I think it's a great thing, and I'm one big. I don't normally disagree with Elon a lot. Anybody knows me knows I love Elon, and I don't want to disagree with him. But okay, so that's the basic presentation on TeslaBot, and there was a Q&A. I broke out the Q&A session and moved it into the different parts. So let's cover, what do we got here? Oh, the very common question was use cases. What is it going to be used for?
Your humanoid context, I'm wondering if you've decided on what use cases you're going to start with and what the grand challenges
Hang on a second.
are in that context.
I did something wrong here. I've never done this before, so okay, here we go.
Humanoid context, I'm wondering if you've decided on what use cases you're going to start with and what the grand challenges are in that context to make this viable.
Well, I think for the TeslaBot, Optimus, it's basically going to start with just dealing with work that is boring, repetitive, and dangerous. Basically, what is the work that people would least like to do? Yeah.
Boring, repetitive, and dangerous. He was asked about use cases. He really did not give a specific example of what he thinks the robots would do. I think it's going to come up later. He gave an example of what it would not be doing. But boring, repetitive, and dangerous. Now, what's interesting is I had my conversation with James Dalma in a previous interview, and James Dalma was saying generalized humanoid robot, and I was saying roofing robot. That a purpose-built roofing robot would be great because Tesla's trying to do solar roof, and if they could install solar roof at lower cost, and roofing is a arguably boring, repetitive, and definitely dangerous task. It's one of the most dangerous jobs, being a roofer. So I think this may be that the generalized humanoid robot that James Dalma was talking about would do the roofing task that I was talking about. We could end up both being right. I thought it would be, they would design a purpose-built roofing robot that would have a different shape and different form. But the way Elon talked about it here, it certainly would make sense to have a generalized humanoid robot take on roofing tasks. And, if a robot falls off the roof and breaks, well, okay, but at least you didn't damage a human. Humans are very, very subject to injury, and so you want to prevent that. And there was another use cases question here.
Well, we certainly hope this does not feature in a dystopian sci-fi movie. But really, at this point, we're saying like maybe this robot can. We're trying to be as literal as possible. Can it do boring, dangerous, repetitive jobs that people don't want to do? And once we can have it do that, then maybe it can do other things too. But that's the thing that would be really great to have. So it could be your buddy too. I mean, if I want to have it be your friend and whatever. I'm sure that people will think of some very creative uses.
So people want to see the robot as something scary, different, weird, funky, whatever. And Elon likes to joke about it that, everybody wants it to be a sex bot. Well, apparently it doesn't have the appropriate holes for being a sex bot. I suppose with 12 actuators in the hands, it could be useful for a specific purpose, but or specific purposes, male or female. But that's not the intent. The intent here is to do boring, repetitive, dangerous jobs. Another really good example that I was thinking of is when I was much, much younger, teenager, I worked at Burger King and Dairy Queen, different jobs where, flipping burgers. If anybody's ever worked inside a Burger King or McDonald's, a lot of the work is actually done by machinery, and then you do some sort of repetitive task after the machinery. Like, so in Burger King, you would slap a frozen burger on a grill, it would go across the grill and cook, and it would come off the other end, and then you would take the burger patty, put it on a bun, put mayonnaise, put whatever the toppings were on the Whopper, and hand it out. Or you would take a bunch of fries and put them in a grill a basket that you dip into oil, and that hot oil is dangerous, and the hot grease coming off the burger grill can be dangerous. One time I got hot grease in my eye. No big deal, but I went to a doctor, got checked out. I was okay. One of my coworkers stuck his hand in the hot oil. He was not the brightest guy. Let's just be clear. He was not the brightest guy. It's a long story. But, I could see where it would make sense. Working in a fast food restaurant is a boring, repetitive. It's not typically dangerous, but it's a boring, repetitive set of tasks. And maybe that would be a good use for repetitive jobs. Yeah. I was thinking, like, I'm probably boring and repetitive. If somebody had to satisfy me, that would probably be a boring, repetitive job. Just ask my wife. Anyway, so, and again, there's comes up again.
The robot is not prompted by specifically by manufacturing needs. It's just that we're just obviously making the pieces that are needed for a useful humanoid robot.
This was a question from Rob Maurer from Tesla podcast, Tesla Daily. Rob asked about whether the robot was designed and conceived to be used for manufacturing in Tesla's factories. And Elon's pretty clear, no, that's not the point. I know a lot of people are talking about Mars. I don't think it's necessarily about Mars. But let's continue with this clip. Sorry.
So I guess we probably should make it. And if we don't, someone else will. And so I guess we should make it.
I mean, part of it was just like, this is sort of the reason for the TeslaBot that I think Elon's, I don't know if sandbagging is the right word here. TeslaBot they just had all the hardware. They have everything they need. They have the hardware and they have the software. The only, maybe they need to make it walk, but that's a relatively easy thing. The real world AI vision, being able to understand the world around it and operate in the world around it and manipulate the world around it, is something that Tesla is uniquely capable of doing. And then a lot of the hardware to make the robot work, the batteries, the actuators, the little motors, there's a lot of these little things that, well, Tesla does that. And the manufacturing of them, well, Tesla does that. Listen to this.
And make sure it's safe. I should say, also volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. It's also important for that humanoid robot.
Okay, this is the big deal. Let me play that bit again. I'm sorry, I think that was really big, and we got to play that again.
And underrated. I should say, also volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. It's also important for that humanoid robot. How do you make the humanoid robot not be super expensive? And
how do you make the humanoid robot not be super expensive? How do you make the humanoid robot not be super expensive? We're really good at manufacturing. We make things at scale. This is what I talked about earlier. Do I have that? The robot is about 125 pounds. A typical Tesla car is about 4,000 pounds. I think the Model 3 is probably under 4,000 pounds. The Model Y is probably close to 4,000 pounds. So this is 1/30th of the weight of a Tesla Model 3 mass. The molecules that go into a TeslaBot, there's a lot fewer molecules going into a TeslaBot than there are molecules going into a Tesla Model 3. The components, there's a lot of components in ElonBits.com for the water bottles and the shirts. I'm wearing insanely gigantic today. And I think TeslaBot, as small as it is, could be insanely gigantic, and that's where I'm going here. If they can make 1.5 million Model Ys a year in a couple years, and Model Ys weigh 4,000 pounds, probably less than 4,000 pounds with the new version, but let's say they weigh 30 times as much. There's 30 times as much mass in a Model Y as there is in a TeslaBot. if they can manufacture TeslaBot to scale and it has fewer components and less mass, then what are the chances? And the FSD chip set is already being manufactured at scale. They're taking the same FSD chip set and putting it in the bot. Probably be the FSD version 4 or FSD computer 2 computer hardware 4 version 2 of the FSD computer going in there. If they can make 1.5 million Model Ys, does that mean they can make 10 million or 50 million Tesla bots a year? I think that point, let me play that again. Let me play that clip again, because I feel like that clip, there's something there. Listen to this clip again.
The robot is not, we probably should make it.
Here we go.
I should say, also volume manufacturing is extremely difficult and underrated. And
Volume.
We've gotten pretty good at that.
We've gotten good at volume
It's also important for
manufacturing.
that humanoid robot. How do you make the humanoid robot not be super expensive?
How do you make the humanoid robot not be super expensive? And the answer to that is you build it at scale. You build millions of them, because you're investing all these resources in making the robot design. And you're investing all these resources ultimately making a factory to build the robots. If you only build 1,000 robots a year, then all those costs are amortized over a small number of robots. If you build the robots at scale and you build 1 million a year or 10 million a year, you're amortizing those costs over a larger number of robots, and that brings the cost of the robots down. And you get economies of scale. You figure out how to produce them more efficiently when you decide we're going to produce these at larger scale. So, a single piece casting for the chassis of the robot is much smaller than a single piece casting for the rear of a Model Y. So you're probably going to see a chassis for this robot cast in one piece. And then there's going to be other components added on, each arm, each leg. And maybe the arms and legs are composed of single piece castings with, the robots and actuators. They're going to find manufacturing techniques to make this thing at scale. And to me, that's a very big deal. And then there's this other detail here. Hang on.
I mean, this is just going to be bot version 1. I mean, we'll see. So
this is going to be bot version 1. They're already thinking about, they're already aware that there will be a bot version 2. This is bot version 1. Okay. And we're going to see this with Dojo. The Dojo that they displayed, they mentioned, well, the next generation of Dojo is coming. There will be a next generation of the bot. And I think ultimately, Elon has some ideas about how TeslaBot will be useful in boring, repetitive tasks. But once they build version 1 of TeslaBot, which would be a prototype next year, once they build version 1, then they will learn from how it interacts in the world. It will train the AI in ways that the cars couldn't, because it will operate in spaces that cars don't operate. It will interact. It will learn from. It will manipulate the world. It will pick up objects, and it will have to learn from manipulating objects. It will interact with language in ways that cars don't. And so the next generation chipset and the next generation Dojo are all going to help train the humanoid robots to be able to do more in our world, to care for the elderly. It's really, I can tell you right now, Monday I'm taking my mother from one assisted living facility to another. And I can tell you assisted living facilities that take care of the elderly and nursing homes that take care of the elderly, they're having a horrible time finding labor. Very, very hard to find people to work in those conditions. It's relatively an unpleasant job. You have to clean up feces, urine. You have to deal with people who are confused all day long. It's a frustrating, I mean, there are people who are genuinely built for it, but a lot of the routine, boring, repetitive tasks that people have to do in assisted living facilities and nursing homes could probably be done by humanoid robots. Cleaning up human waste. Wouldn't you rather have a humanoid robot cleaning up human waste than a human have to do it? A lot of potential here for this to go on, but let's go on here. Sorry.
It needs to be able to do things that people do, and be a generalized humanoid robot. I mean, you could potentially have it give it like 2 fingers and a thumb or something like that. For now we'll give it 5 fingers and see if that works out okay. Probably will. It doesn't need to be like have like incredible grip strength, but it needs to be able to work with tools. So, and carry a bag, that kind of thing.
So the question was, how do they choose to use 5 fingers? Why wouldn't they use less? And I think that my guess is that there are already robotic hands that have been developed for a while that have 5 fingers. So it's sort of a straightforward format. I could easily see where it would make sense to go to, a thumb and 3 fingers or a thumb and 2 fingers, that might make sense at some point. It's not clear, how much we need the pinky finger, right? So, and if the best part is no part. If it ends up being that the pinky finger is unnecessary and you eliminate 2 actuators on each hand, you're reducing the manufacturing cost of making the thing. Yeah, that would make sense. Maybe 6 fingers is better. Mark Plott says, I agree, Mark. Maybe that's it. So, really interesting stuff there. Let me see what else I had here on TeslaBot. Is that it? I think that was all I had on TeslaBot from the clips. So I'm going to move on to Dojo, which I think Dojo is more important than, see what we got here. I got so many clips. This is crazy. So, no. Okay, I think we're going to start here.
And this gave us our high performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8. And it is backed by 1.25 megabyte of fast ECC protected SRAM and the low latency, high bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch.
Okay. What he's talking about here is not the Dojo chip. What he's talking about here is what he calls a node. And this is a part of a Dojo chip. The Dojo chip is actually a bunch of these together. As I understand it, the Dojo chip is actually a bunch of these together on one chip. Just want to be clear about that because I think this is really important. We're going to go more into this in a second.
More than 1 teraflop of compute in our smallest entity of scale.
So this is what he calls the smallest entity of scale. This is a training node, and an individual training node can do 1 teraflop of floating points. Was it BF16 or CFP? I don't know. There's this. A teraflop is a lot. This is a fast. This alone is a fast computer, and this is part of the chip. So let's go forward and see what else we got.
When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops.
So that's those initial nodes that was a teraflop. You put 354 of them together, and this is the chip. Okay, like the node itself is already a pretty powerful computer, but 354 of them on one chip. Oops.
When we click together 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses.
So you have individual nodes on the chip, and there's high bandwidth communication between the nodes on the chip and off the chip. And then you have high bandwidth communication around the edge of the chip to go from the chip off chip. That's the 4 terabits per second edge off chip bandwidth.
576 of them to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today.
So, and he's going to talk about this. Networking switch chips are the top level high performance chips for throughput and for networking throughput for bandwidth, and this has double that.
Network switch chips are supposed to be the gold standards for I/O bandwidth. If we put all of it together, we get training optimized chip, our D1 chip. This chip is manufactured in 7 nanometer technology. It packs 50 billion transistors in a miserly 645 millimeter square. One thing you'll notice, 100% of the area out here is going towards machine learning training and bandwidth. There is no dark silicon, there is no legacy support. This is a pure machine learning machine.
So what we have here is a purpose-built chip that we have a purpose-built chip that is designed specifically for neural network training computing. And little detail here, the chip that is in the car is what's called an inference chip. And Dojo and the computers that are in the home office that take the data from the chips and then send out instructions to the chips how to change how they interpret the world. Those are neural network training chips. So they're two different kinds of chips. And these chips are optimized for the training function within neural network training, within machine learning. And this is a point that's going to come up later, that GPUs are the current type of computer that's used. Let me see if I have that right here. Let me play that clip. Give me a second. I'm sorry. Again, I'm sorry because I'm like all over the map here because I've never done this.
Is it actually better than GPU cluster or not? But then beyond that, it's basically a generalized neural net training computer. But it's very much optimized to be a neural net. So, CPUs and GPUs, they're not made to be. They're not designed specifically for training neural nets. We've been able to make GPUs especially very efficient for training neural nets, but that was never their design intent. So it's basically GPUs are still essentially running at neural net training in emulation mode. So with Dojo, we're saying like, okay, let's just ASIC the whole thing. Let's just have this thing it's built for one purpose, and that is neural net training. And just generally, any system that is designed for a specific purpose will be better than one that is designed for a general purpose.
So, kind of like I understand it. I'm trying to figure out how to explain what he's saying there. The most common type of computing chip that is used for neural network training is called a GPU, a graphics processing unit. If you have a Windows machine, a gaming machine in particular, you probably have a GPU on it. And the GPU is particularly good at taking the information from at projecting images on the screen at high resolution, high frequency, so you get a realistic image. And basically it's designed for graphics. And it's been repurposed. GPUs have been repurposed to be used for neural network training. I believe that Google uses something called a tensor processing unit. And that's another type of chip that may be designed for neural network. I don't know if that's designed for the inference chip or if that's designed for the training. But what the Tesla team did was they said, listen, we have a very specific purpose and we're trying to accomplish a very specific goal. And AI training, and if you follow ARK Invest, their big ideas, their most recent big ideas white paper, they are predicting that AI training is going to be a monster industry in the future. That we're going to see machine learning grow. There's a little bit of a conflict, by the way, in the course of the presentation. Elon kind of poo-poos machine learning for most applications, where Andrei Karpathy, I think, thinks machine learning ultimately will have much broader uses. I think it's over time we're going to see machine learning grow, and Elon maybe concedes that when we have the robots at scale, maybe the robots will be using machine learning, and then it will become a much broader application. But this concept of an ASIC, an application-specific integrated circuit, this is something that's been around for a long time in the computer world, and you can use a generalized computer to get something done, and then you have to write software to make the generalized computer do the specific task. But if you can design the hardware so that the hardware is designed to do that specific task, it's much, much faster. So the tensor chip, I think there's more than one kind of tensor processing unit. I don't think it's just in the Google mobiles, but I'm not sure. So it's that AI training is such a specific task, and Tesla has such an intense demand for really, really good AI training right now for FSD, then for the robot, humanoid robot, and in the future for other, as machine learning expands, for other machine learning tasks as that grows. So let's good with that. Let me see what we got next. Okay, so I don't think we finished here. Let's go back to the chip.
And this is the D1 chip in a flip chip BGA package. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package. This chip is like a GPU level compute with a CPU level flexibility and twice the network chip level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par.
You can see that the Dojo chip, this is on the vertical axis is the off-chip bandwidth, how fast the chip can move data on and off the chip, how fast data moves on and off the chip. And then to the left and right is the teraflops of the chip. So it's not that the Dojo chip is that fast in terms of teraflops. It's a little bit faster than GPUs and startup chips that are out there, but it's the bandwidth that's where it really stands out. Now, I think also the teraflops are more effective. Teraflops are an awkward thing because the GPU has high teraflops, but it has to run them in emulation, so that means they don't use their teraflops as efficiently. So the Dojo chip, he didn't mention this in this part of the presentation at least, but the Dojo chip, number one, has more teraflops. It's a faster chip overall, and it's able to use those operations more efficiently, and it's able to communicate the results of its operations and bring in data much faster, much faster. This is a dramatic, let me see if I'm covering that bit. So it's 5x the speed of a GPU in terms of bandwidth on and off the chip. So this is very important, and we're going to see, because of modularity, we're going to see where this goes shortly. Let me move on. We're going to head to the tile.
This is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile.
Okay, just really quick. What we're going to see here is not that much of a surprise, because on the AI Day invitation, there was this image, and the image was of what we're about to see, which is the assembly of this tile. And James Dauma, I think it was in an interview with Dave Lee, he broke down what he saw, and he roughly predicted what we're seeing here, what was presented in the presentation, that we just talked about the D1 chip, which is 300 and some nodes on one chip. And now we've got 25 of these chips together on this tile. And then the reason that I keep talking about bandwidth and they keep talking about bandwidth, the reason bandwidth is important, particularly for FSD, and what will be important for the humanoid robot as well, is you are funneling in 8 cameras running at something like 60 hertz, as in 60 frames per second, 1280 by 720 or 1280 by 960 or something. So it's like a megapixel, 8 megapixels times 60 seconds. So it's a huge volume of data that you need to process. And then they want this to be able to process multiple streams. They want to be able to look at multiple video streams at the same time. They identify comparable clips so that they can learn from the encounter. So bandwidth is really important for processing all this video data. That's why Dojo matters so much, and why Dojo, and we're gonna hear a lot more about Dojo. I'm sorry, this is like a massive Dojo story.
And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This perhaps is the biggest organic MCM in the chip industry, multi-chip module. It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality.
So this is reality. We're about to see it, but part of, you have to remember the purpose of AI Day. The purpose of AI Day is recruiting, right? They want to, the stated purpose of AI Day is recruiting. They want engineers, hardware engineers, software engineers, neural networks, particularly neural network software engineers, but hardware engineers, and I think for Dojo, and this is about hardware engineers. They want to recruit hardware engineers, and they want to show you we're dealing with really, really hard problems, and we're coming up with really, really cool solutions. And if you want to be at the true cutting edge of the latest technology and be doing the coolest work that's out there, then come work for Tesla. And this is where you're going to change the world. This is where you're going to be doing really cool stuff. This is an absolutely amazing thing that they're doing here. So now the tile is 9 petaflops with 36 terabytes per second off the tile. All right, let's move on. So we're going to move on to the next one. We're still working on the tile.
We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here.
This is still engineering of the tile, right? You've got the chip, which was engineered to be very, very fast and very, very efficient. And now we've got to get power to the chips. And we got 25 chips on one tile, so we got to get power to the chips. So we're doing this. We've got the networking hardware to get the data on and off the tile. And here's more.
Here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling.
Orthogonal, for those who aren't mathematical, orthogonal is like perpendicular. So the compute plane is flat, and the heating and power, the cooling and power are orthogonal. This is the plane that the chips are in, that all the compute is happening in this roughly two-dimensional space, and the power comes in from the bottom, and the heat goes out through the top, and there's liquid cooling, and we're going to hear more about this in a minute, but
that makes high bandwidth compute planes possible. What it is a 9 petaflop training tile. This becomes our unit of scale for our system.
Unit of scale for our system. This is, they start with the unit of scale for the system. So they start with the node, and then they build a chip that has 300 and some nodes on it, and then they build a tile that has 25 chips on it. And you can see how this is getting bigger and more amazing. And this is where they start to scale. They can add more and more training tiles to make a more powerful computer. And I think this is a good moment to cover this one bit about power coming in, cooling going out. So let me just pop this clip up from Q&A.
So from a thermal standpoint and power standpoint, we've designed it very modular. So what you saw on the compute tile, that will cool the entire tile. So once we hook it up to, it is liquid cooled on both the top and the bottom side. It doesn't need anything else. And so
this was in response to a question about how are you managing to keep the chips cool, because this is a fundamental problem with computing is when you have very high powered computing, they generate a lot of heat and you need to remove the heat. This is, people talk about space and we should put servers in space. Figuring out how you're going to keep your chips cool is really important, because if they run without cooling, they will melt. right? They will get so hot they will melt. Maybe they'll start a fire or whatever. So keeping the chips cool, keeping the hardware cool is a very, very important task. I'm not saying they have to be ice cold, but you can't let them get too hot. You have to be able to get them cool. And so they engineered this whole tile. They're not cool. They're not cooling at the chip level, which is pretty common. Like in the computer that I'm running this live stream on, there's a heat sink on top of the chip. They're running like a whole 5 chips together, and I think maybe by economies of scale, they're able to cool more effectively by running 5 chips together, 25 chips together, and cooling them all together.
When we talk about clicking these together, once we click it to power, and once we click it to cooling, it will be fully powered and fully cooled.
And I think the question was, how do you cool all of them when you have all of these things together? And the idea is each tile is designed to cool itself, and so you can put tiles together, and since each tile cools itself, you don't have to worry about cooling the whole group. You don't have to worry about cooling the whole room. That's not a huge issue, because when you cram a whole bunch of computers together, they're generating a lot of heat. Now you've got to cool the whole room. If you've got your system working at the tile level, then it solves itself as you scale up.
And all of that is less than a cubic foot.
That's kind of an interesting detail, that the tile is a cubic foot. I'm not sure what they meant about the cubic foot. Normally a cubic foot is 1 foot tall. The way I think about a cubic foot is it's 1 foot tall and 1 foot wide and 1 foot deep. And I think this is probably a cubic foot, but it's not a cube. It's probably a flattened area. I'm not sure. I think the cubic foot he's talking about includes the cooling and the power.
Yeah, so Tesla has a lot of expertise in power electronics and in cooling. So we took the power electronics expertise from the vehicle powertrain and the sort of the advanced cooling that we developed for the power electronics and for the vehicle, and applied that to the supercomputer.
This is really, really important. This is one of the, I like Tesla, and I'm a Tesla stockholder. Full disclosure, I own a ridiculous amount of Tesla stock, and matters a lot to me if Tesla's successful and if Tesla stock goes up. Although I'm not planning on selling for 10 years, so it doesn't matter a whole lot right now. I can't access my IRA for a while, so I don't really care in the short term. But I'm really an Elon Musk fan. And what's really striking is how Elon Musk they develop technology in one area and they use that technology somewhere else. So they've used SpaceX engineers to help with material science for Tesla, and they're using Tesla Model 3 motors and battery packs in the Starship Super Heavy to manipulate the grid fins. The ability to cross over what we've learned in one place and apply it in another place is something that a lot of organizations are not very good at, and Tesla's really good at it. And a central reason why Tesla is so good at it, and SpaceX is so good at it, and Boring Company and Neuralink are so good at it, is because this guy right here. Can you imagine any other CEO of any other major company who knows artificial intelligence, machine learning, hardware and software in depth, and knows manufacturing of cars in depth, and knows performance characteristics of cars in depth, and how the seats are made? He was talking with Sandy Monroe about how the seats in the new cars are so much better, and the carbon fiber wrapped rotors in the Plaid Model S, and then you get to SpaceX, and he's designing rockets, and he's in the details. You can watch the Everyday Astronaut video, and he's talking about how the Raptor engines are being redesigned and how the Starship is being designed with. There's no industry CEO in any one company who has this level of knowledge about just their business. He's got 4 different companies, and Tesla is like 3 different companies itself. And SpaceX is really at least 2, maybe 3 companies, because it's got launch, it's got Starlink, and it's got exploration and manufacturing. There's so many things, and because of him, all of this comes together. And it is the one thing I worry about, is if you lose Elon, does that cross-department flow of information get lost? And I think it's important that you have Drew Baglino, you have key people at the top, that he's baked this into the culture of the companies, is that they work together. And I think this is an absolutely tremendously important feature of what makes Tesla a great company, what makes SpaceX a great company, what makes Elon. And I'm blunt. I'm like the biggest Elon. I'm not the biggest Elon Musk fan in the world, because he's got a lot of fans, but I am an absolute Elon Musk fan. He is the driver of this tremendous innovation.
because as you point out, getting heat out is extremely important. It's just really heat limited. So, yeah, so it's funny that like at the compute level, it's operating at less than a volt, which is a very low voltage. There's a lot of amps, so therefore a lot of heat. I squared R is really bites you on the ass.
You know, he's dropping physics equations or physics. It's not an equation. He's dropping physics relationships, physics calculations in the middle of a presentation. He goes from physics to neural networks to it's just absolutely amazing. Anyway, sorry. Let me get back to. I just wanted to, because we were talking about cooling in, I think it was the previous clip. I just wanted to bring that back to that. I think this is the one we just did. Oh no, okay, here we go. Here's the actual tile. So this, I'm not sure what the cubic foot is. I don't think that's a cubic foot. I think that plus the cooling and the electrical going in, I think this goes into some sort of, that alone can't be a cubic foot. I mean, maybe my math is off, but I don't see that as a cubic foot. So there's got to be something more in there. Maybe that is a cubic foot. I don't know if anybody has a sense of proportion there. I think there's more going on that takes up the cubic foot, but I could be wrong. Anyway, but it's real. This is actually real. This is like a prototype, basically, an early version of it. But
I can't believe I'm holding 9 petaflops out here.
9 petaflops, but he's going to show you. Is it right here, or is it I think it's the next one. The next one is.
Last week we got our first functional training tile, and on a limited cooling benchtop setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on Dojo.
So GPT, for those who don't know, is as I understand it, and we're pushing the limits of my understanding, GPT is some sort of machine learning. It says GPT math. I know there's a GPT for language, and this is MinGPT. This is something that Karpathy created, and they're running Karpathy's machine learning algorithm programming on Dojo, and it's working, and it's succeeding. Now, I was mentioning earlier on this side over here, I was talking about the cubic foot, and here you can see the electrical going in and the cooling. The black hoses are the cooling coming off, and the blue cabling, I think, is the power going in. So this is probably not the final form of how I think this is sort of like, all right, let's take this thing and let's see what we can run on it. And they were able to run a training tile on it. Now they've got to build the cabinets, and they've got to build how they run all the wiring. I think sure they already have plans of how they're going to do it, but that's where they're at with that. So let's go back to the next thing. So that's the tiles. Now the next step is the Exapod.
We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No.
So what you're seeing there is they're planning to put 6 tiles together on a tray, and then 2 trays in a cabinet. So I think that means 6 tiles up and 6 tiles down. So a cabinet is going to have 12 tiles, right? So 100 petaflops in a cabinet, 12 times 9 is a little over 100, and 12 terabits per second bandwidth. So this is, you can sort of envision what you saw just a minute ago with the black hoses and the blue cables. You're going to have that refined and done in a less ugly manner on a massive scale with 12 of these. But wait, this is where it gets good.
We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this,
the Exapod.
we have an Exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here.
Remember, one node was a teraflop, so 1 million nodes is an exaflop. An exaflop, and exaflop, sorry, I actually had to look this up because I wanted to make sure I understood. 1 exaflop is a goal that people have been trying to reach for a supercomputer. As far as I know, this might be the first exaflop computer that is, well, it's not, of course, it's not complete yet. There are others who are working on exaflop computers, but keep in mind what I said before. Exaflop, flops is a measure of how fast a computer runs. I think it's floating point operations per second, something like that. So a teraflop is 1 trillion floating point operations per second. A petaflop is 1 quadrillion floating point operations a second. An exaflop, quintillion floating point operations per second. So this is sort of, but keep in mind, it's not just that it's an exaflop, so it would be the fastest supercomputer possibly in history, but it's a specific to a task exaflop. So for the purpose that it's designed, it's going to be faster than anything conceivable. Massive bandwidth, massive performance, low latency, all the things that you want for this to achieve. Okay, so that was the Exapod. What else did I want to cover here? Okay, we got a summary.
To add to new levels of performance. To sum it all, this is what it will be. It'll be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint.
I'm not sure what he's comparing it to. So 4 times the performance of some other training computer. I don't know if he means the training computer that Tesla is currently using that uses GPUs, or if he's referring to some other known AI training computer that's out there. In the middle there, you see 1.3x better performance per watt, which basically means it's more energy efficient. That's not a huge difference, but it's something. And when you're operating at this scale, you're saving a significant amount of energy. And 5x smaller footprint, that's always been a thing with Elon, is can we do more in less space? And I think he said earlier that it was 10 cabinets. So pretty, that's, somebody says that they're 120 cubic feet. I think that the cabinets are probably more, let's see, 6 tiles in a cabinet would be 6 cubic feet. My guess is that the cabinets are bigger than 6 cubic feet. But I don't know, maybe it's 12, maybe you're saying, 12 cubic feet, right, 12 cubic. My guess is the cabinets are actually bigger than that. But anyway, there's more to this clip. Sorry.
This will be Dojo computer.
And that's it. This is the Dojo computer, fastest AI training computer. Okay, and there's this one bit more.
And we are not done. We are assembling our first cabinets pretty soon. And we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again. We will have this journey again. We're recruiting heavily for all of these areas. Thank you.
So again, this is a recruiting effort because, okay, this is what we've done and this is what we're about to put together. And they have a team that's pretty much good enough to finish the job of putting together Dojo. I think they're still recruiting, they're working on building the first cabinet. There's still going to be work to be done. There was a point in the Q&A that I don't think I saved the clip where one of the engineers for putting Dojo together was asked about whether they've solved all the problems yet. And they haven't solved all the problems, but they can see the path to solving all the problems. This is a common thing I've seen with Tesla. Drew Baglino was talking about the rollers on Battery Day. Again, Elon knows about battery production like crazy, but Drew was talking about the rollers and it's not a science problem, it's an engineering problem, and we'll work around it and we'll work through it. And they're working through problems. But if you are a hardware engineer, a computer chip hardware engineer, and you want to work on the latest, the greatest, the coolest, the most interesting type of work you could do, then Tesla is the place for you. And that's the purpose of AI Day. And Wall Street it's going to be looking at TeslaBot, and they're going to be saying, oh, maybe Cybertruck's late. We'll cover that later. But that's not the story here. The story here is that they have just built the top AI, or they are building the top AI training supercomputer. And what I love is, and you see this with Tesla from time to time, we're not done. And here you go. Next generation will be coming too. Once we get this built, we're not stopping. And I don't know whether the plan is, okay, we're going to build, 120, was it like 10 cabinets, so 120 tiles. And I don't know if the plan is once we do that, well, we'll build more dojos. But they're probably going to build more dojos. They probably won't just build one generation, one dojo. They'll build multiple ones of those. Somebody suggested they would have to put one in China because China might not want the data from China going somewhere else. Who knows? National security. So we put a dojo there. But you're actually going to see probably 2 or 3 of these dojo computers, or maybe they'll just make it bigger. Maybe they'll just go from 10 cabinets to 20. But then the next generation dojo will be coming. That will probably be more power efficient and more flops and better in other ways. And to some extent they learned from the first dojo. What can we do better in the next dojo? Really, really cool stuff. Let's see if there's anything else here with Dojo that I wanted to talk about. Oh, 500,000 nodes.
Let's see.
I
Since
think I missed this
D1
before.
chips can seamlessly connect without any glue to each other, we just started putting them together. We just put 500,000 training nodes together to form our compute plane.
This is the idea that they took the tiles. The tiles are basically a representation of connecting all the D1 chips together. Sorry.
This is 1,500 D1 chips seamlessly connected to each other.
So you have, I think it's 120 tiles. Each tile has 25 chips. So I think that's how you get the 15. I got to do the math there. 120 times 25. I guess that works out to 1,500. I can't even do. I'm like so overwhelmed. For those who don't know, like I stayed up late last night working on these clips, and I couldn't go anymore. And I slept like 4 hours. I'm gonna do a Sunday live also. Yes, Ape Nation. There will be a Sunday live. I spent like 4 hours. I got 4 hours of sleep, and then I woke up and I got right back to putting these clips together. And we're pretty quickly we're gonna have to move to the okay. I got to start throwing these clips in, and it's gonna get a slow down a little bit as I incorporate the clips because I couldn't get all the clips together in time for the video. But there's one more thing here where there was a Q&A with Elon at the.
Yeah, I guess the proof's in the pudding. So we should have Dojo operational next year, and I think we'll obviously use it for training, video training. Fundamentally this is about like the primary application initially is we've got vast amounts of video, and how do we train vast amounts of video as efficiently as possible, and also shorten the amount of time. Like if you're trying to train to a task, like just in general, innovation is how many iterations and what is the average progress between each iteration.
This is really important.
And so if you can reduce the time between iterations, the rate of improvement is much better. So if it takes like sometimes a couple days for a model to train versus a couple hours, that's a big deal.
This is something I've been talking about why I think Dojo is really, really important for the development of full self-driving. Is currently we see that the iteration from they distribute version beta FSD beta version 9.1, and the plan is every 2 weeks there'll be a new update to the software. And the question is, now he's talking about training a model. That's not training the model that's going right out to your computer, to your car. But there's a whole bunch of models that they're operating that ultimately go together to get shipped out to your car to make your car work better, the Tesla FSD work better in the car. And if it can train, right now it's a 2-week cycle for updating the software, and they can go from the typical model that they train takes 2 days to the typical model they train takes 2 hours. That's 24 times as fast. And so maybe when you put that all together, maybe instead of having an update every 2 weeks, maybe you start having an update every 2 days, or maybe it's every day. Or maybe the quality of the updates is significantly better and it's an update every 2 or 3 days, but the updates are bigger jumps than you were getting in 2 weeks before. that is a lot of what's going on. Let's keep going.
But the acid test here, and what I've told the Dojo team is like it's successful if the software team wants to turn off the GPU cluster. But if they want to keep the GPU cluster on, it's not successful.
So it's all great. This is a hardware project, and the hope is, and I'm sure they're confident of it is, but the hope is that Dojo is so good that they have these other 3 computers. Did I have that on here? I don't know what I did with that clip. I think I had a clip somewhere where I had, I don't know where I have that. See if I have this clip. I don't think I do. I had this clip of, pre-Dojo. Let's do pre-Dojo right here. Sorry.
In scaling our neural network training compute dramatically
this is going to take me a second to get this right. This is where I run into my problems.
Barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. In scaling our neural network training compute dramatically over the past few years. And today we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world.
So this is the current state of the neural network training computers that they're using at Tesla. And I meant to show this earlier and I got messed up. So you can see that there's an auto labeling GPU cluster that has 1,700 GPUs. This is on the right, on the side of the screen opposite. Let me move my head over. I guess that'll. Right here you can see 1,750 GPUs, 752 that's doing auto labeling, and then there's 4,000 GPU cluster that's doing training, and then there's a 5,760 cluster GPUs cluster that's doing training also. That's the compute that they're doing now, and you can see what they're trying to do. Let me play the clip again, so see if I can understand it better.
In scaling our neural network training compute dramatically over the past few years. And today we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. In scaling our...
I think he said it's more than the top, they have more GPUs in their neural network training clusters than the top 5 GPU clusters in the... Let me play that clip again.
Is more than the top 5 publicly known supercomputers in the world. In scaling our...
More than the top 5 what?
Is more than the top 5 publicly known supercomputers in the world.
More than, okay, I didn't hear it. More than the top 5 something computers in the world. Maybe it was neural network training computers. And there was one more clip from Milan. Let me get this off the screen.
Well, first, we have been scaling our capacity to evaluate our software and neural network dramatically over the past few years.
Right.
And today, we're running over 1 million evaluations per week on any code change that the team is producing. And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated cluster.
So they actually have 3,000 of the FSD chipsets, or I think it's actually 3,000 of the FSD hardware that's in the car running in data centers, and they're testing 1 million runs a week. I think this may be the simulations, or maybe they're running models on real world data to see how it's going to perform. Wasn't really clear, but this is just the extent of hardware that Tesla is throwing at the FSD problem is like, I don't think anybody is close to what Tesla is doing in terms of throwing hardware at a very, what seems like a very, very narrow problem. It's a very, very narrow problem that happens to be very broad once you get into it. And maybe that's true of everything in life. Okay, so I got to move on. I think I've covered everything that I had in Dojo. Let me just check quick to see if there are questions about... I don't think I have answers, so let me... when does your PC have a D1 chip? Let me just address that. That's a really good question. I just want to address that. The Dojo chip is not something you're going to want on your computer. The Dojo chip is designed for a very, very specific purpose, which is neural network training. And your home computer, you're not using it for neural network training. You might be using it to play video games. You might be using it to, there was actually a question in the Q&A that I think I was going to talk about it. I'll talk about it now. There was this question like where this guy seemed to be asking if they would ultimately put the Dojo chip in the car. And it misunderstands that, no, that's not the point. The Dojo chip isn't designed to drive the car. It's designed to train the chip that drives the car. That's the, it's designed to process video data and use that video data and other data, annotated data, whatever, to figure out how do we train, the reward functions and everything. How do we figure out how do we use this data to train the FSD chip to drive better? And it's not something that you would use to run a video game. I mean, maybe it could run a video game, but then you would be doing the reverse of why this is an advantage over GPUs. You would have to like create software to do something it's not designed to do. And it would be a fast computer and would figure it out, but it's not, that's not the purpose. The purpose is AI training, AI training, AI training. And AI training ultimately is going to be much broader than FSD, and it's going to extend to the robot, but there are going to be other applications for machine learning training, and this is optimized for, as far as I can tell, for all of that. And then the next generation Dojo will be even more optimized, or maybe capable of doing more. We'll see. So let's move on. And we're going to slow down a little bit because when I put these clips in, it's going to be a little awkward. So let's start with I think we'll start with Karpathy.
And
give me a second here. Every time I put one of these clips in, I got to get the audio on.
And I'm incredibly excited to be here to kick off this section.
Okay, so this is Andrei Karpathy. I'm just going to run him without my face.
I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself.
It'll be a mess. All right, so this is Andrei Karpathy. For those of you who are new to this, congratulations. I use special lights. Isn't that cool? I don't think I even turned on my other lights. A little more light. I'm doing everything wrong, folks. So this is Andrei Karpathy. Andrei Karpathy is head of the Tesla Vision team. He gives a lot of talks. If you search YouTube for Andrei Karpathy, Andrej Karpathy. Karpathy, he is like a legend in the machine learning community. He's a legend in neural networks and AI, and brilliant guy. And so I'm going to go through what he said about what they're doing. And I'm not covering everything he did. I'm trying to, if I covered everything in AI Day, this video would go on for a lot longer than it's going to go on. I think we're already going over an hour. I think we're going to go 4 or 5 hours today. But if I covered everything, I just tried to pick out. Karpathy's talked about a lot before, so I didn't want to cover things he's talked about before. So anyway, let me bring up the next clip. Let me shrink myself. Trying to make this insanely gigantic, but okay. What is that? I know what that is. Okay, so let's bring in another clip here. Not that one. There's just different bits where. Let's do this one. Hang on, I got to get
this. Also improved a lot of our
audio
object
working.
detection.
Every
so, for
time.
example,
This
here
is gonna be frustrating
in this video,
for me, but
I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't.
Let's go back here. So this is FSD is looking at multiple cameras. And the earlier versions of FSD would look at 8 different camera images, 8 different still images at a time. And the labelers and everything that was done 1 image at a time. 8 images are coming in simultaneously, and it made the processing really slow. So there's different things they did. So here what they've done is they've, the lower left, move my face around so I can, on this side here, this is what the computer sees in vector space when it's operating off of 8 images. And this over here is what the computer sees with the update, where they're looking at all 8 images at the same time that they stitch them up into a vector space in advance and then have the neural network operate on it. So let me play this clip.
This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions.
What you're seeing here, there's blue rectangles and there's orange rectangles. And the blue rectangles, they're both meant to represent an object that the vehicle that the self-driving software and hardware sees on the road. The orange one is when they were using single camera at a time, and the computer's trying to put together information. The neural network is trying to put together information from all the different cameras at the same time, separately. And the multicam is when all 8 video streams are integrated, and it gets a 3D picture coming into the neural network, or a multi-camera picture coming in the neural network. And so you can see as the blue rectangles are smaller. Let me play the clip again.
This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue.
So you can see that the car that's right in front of it should look the way the blue rectangles show it, but when in the previous generation of how it worked, you got these weird ways that the vehicle looked, and it was seeing it wrong, basically. And all right, let's skip to the next clip, because the next clip I think is going to show this well. Because now we're going to add in video. Again, I got to fix the audio.
The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where.
Okay, here we go.
The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are 2 cars over there, and one car is going to drive by in a.
The 2 cars he's talking about is on the opposite side of the street. You're looking straight ahead, you see 2 cars that are on the opposite side of the street. And what's going to happen is you can see I'm talking about the images at the top. Let's go here. I'm talking about this right here. You can see these 2 cars that are in the image. Okay? And then you can see these 2 cars are right here. And here's ego. The red car is you. And this is the cars, these are all the other cars driving around you. And you've got these 3 cars are going to come across and block your view of these 2 cars over here. Hope that made sense. Let's go back to it.
Include them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us.
Did you see that? Let me play that again. Watch the orange squares. You see in the red circle, watch what happens to the orange rectangles when they get blocked by the cars coming across in front.
The cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account.
Okay, I'm going to try to explain this. I think I understand it. So first of all, in the previous part I was talking about, you would see different orange rectangles because different cameras were telling the software where the car was in different places because it was confusing. And when you stitch all the cameras together, it does better at figuring. Now they're placing the object in the same place because they're all working together. Now, this one is about video. So this is not just looking at an instant of time, but you're looking at several frames before and eventually after, really before. When they're doing the training, they can actually look ahead. That's something we're going to come up on later. But I think that's actually in a different, that's not Karpathy's talk. But by because you knew in the previous frame where the car was, you know it didn't jump. And if you know, well, that car was in that position for 3 frames in a row, it probably didn't jump 100 feet away. But if you're restricted to individual cameras and individual frames in time, then the guesswork for the camera, for the software to try to figure out where the object is becomes very, very complicated. When you combine having multiple cameras, so you have multiple cameras telling you where the same, working together to decide where the object is, and then you have video to say, well, this is where it was before, it probably didn't move that far, then you're able to get much better predictions about where vehicles are. And this is going to come up, where it's going to come up later. It's going to come up later. Okay, so let's move on to the next one, which is, let's do vision versus radar. What's this one? Let's do this one first. I think this is the one that was before.
We are seeing what we had before, and on the right, we're now
gotta
seeing
fix the
significantly
audio
improved
again.
predictions
This is
coming
awful.
directly out of the neural net.
Won't
This
take
is a
me that long, I
multi-camera network
apologize.
predicting directly in vector space, and you can see that
Okay, this is, I meant to show you this first. I apologize.
it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team.
What you're seeing here is you've got these 3 camera images looking forward of what's happening, and then the old version was rendering this in vector space as this blurry mess, and the new version is rendering the vector space very cleanly and making it much easier to drive. So it's very hard to navigate when you have this blurry vector space. You don't know where you're going. Here, it's much easier to navigate. This is how FSD has improved over time. So let's watch this again.
We are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. We are seeing what we had before.
So again, a lot of references to the team. Again, this is about recruiting. We've got, this is a software side of things. This is not the hardware side of things. The software side of things, figuring out, okay, how do we use the inputs we're getting from the hardware to do a better job of describing the world around us and predicting where objects are going to be. And this part right here is just describing the world. It's identifying lane lines, right? This part is just about identifying lane lines. They're doing a lot of other things, but it's just isolating here. This is how it's identifying where the lane lines are and seeing where things are on the road and where the curbs are. The red are the curbs and the blue are the lane lines, or where you're supposed to be going. So that was pretty. Let's see. All right, let's pull up something else here. All right, so now I want to go to, vision versus radar. I didn't put this in yet.
Take that into account.
Let me nail this.
We also saw significant improvements in our ability to estimate depth and, of course, especially velocity. So here I'm showing a clip from our remove the radar push.
Okay, here we go. We're moving on from that last clip. Now we're gonna watch some driving with snow falling off cars.
We also saw significant improvements in our ability to estimate depth and, of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal.
So this is the point where there's a lot of people who were concerned. A lot of people in the Tesla community and outside the Tesla community were concerned that getting rid of radar was going to mean that the car wouldn't perform as well. And you need radar, you need radar, you need radar. And here, Karpathy is showing, so the orange line is the old way that FSD worked using single frames of cameras and trying to assess the single frames independently. The green line is vision with radar, and the blue line is vision without radar. And what you can see is the orange line was way off, and you needed radar to more accurately predict longitudinal depth. How far away the object is the top line here. This is longitudinal depth up here, and then this is velocity. How fast is the object going? And he's saying you can't really predict velocity with single frames, single static frames. But what you're seeing is that the blue line and the green line are basically the same. So radar is not adding anything of value, of any meaningful value. Blue is so close to green that the vision only approach is so close to the vision plus radar that there's no need to use radar anymore. And he doesn't talk about it here. I've seen it talked about in the past. There's a cost to using radar, not just a cost in terms of radar costs money, but there are moments that I've seen in other presentations where radar created problems, and you're eliminating the problems with radar. So that wasn't the snow on vehicles. Sorry about that. I think the snow on vehicles is a different thing. So this is it must be a different speaker. So this is time
Basically.
and distance cues.
So here's a cartoon diagram
Let's get this.
illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming.
Okay, Okay, so we'll listen to Karpathy here. So this is, we're watching a car. There's a couple of key details. The car, oops. Uh-oh. Okay. The car over here, there's a car is going to come up. It's going to come into this left turn lane and approach this intersection. A bunch of stuff is going to happen at the intersection. I'll let Karpathy explain it.
So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom.
That blue car just comes up. That's the ego car, or that's the car that we're concerned about that is driving.
And coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter the features into the queue, say, every 27 milliseconds.
27 milliseconds is 27 thousandths of a second, so roughly 40 times a second.
And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module.
So you've got the way I thought of self-driving before was and the way I think the way that self-driving is originally thought of was that it's making decisions based on what it sees in a given moment. And what Karpathy is talking about here is not only do you need to make decisions based on, you need to include time. So what happened a half second before, what happened a half second before that, or a quarter of a second, or a tenth of a second before that. And if you saw an object across the street and then a car goes in front of it, you don't see it anymore, you should realize it's probably still there. And after a certain amount of time, your vision's been blocked long enough, you don't know where it is anymore, but there should be some persistence of that object was there and it was traveling at this speed, and you're sort of estimating where I think that object was going. And probabilistically, it may be going this path, it may be going that path. And you have to have some sort of cue, some sort of length of time over which you retain that information and evaluate that information. And not only is it for time, but it's for distance. So you pulled up, you entered the left turn lane to make a left turn. If enough time passes, maybe you would push out, because let's say you're stuck at the light for 5 minutes. For some reason, something happens in the intersection, you don't get to go through the light. Maybe you would forget that it was a left turn lane. You have to retain based on distance and time, remembering not just what you saw, but in time 5 seconds ago, but you might need to remember what you saw on the road 100 meters ago or 10 meters ago. That's a really stark difference. And like, that's the kind of thinking that, like, this is why you want to be on a team like this. This is why, if you want to work for the coolest people in the world, be doing the coolest job in the world, and you've got the chops for doing AI training and thinking about these bigger issues, then Tesla is the place you want to work. Really amazing. Okay, one more. I think let's talk about this one.
Yes. So definitely,
And this is Karpathy.
this architecture has definitely
talking about the
complexified from just a
future.
very simple image-based single network about 3 or 4 years ago and continues to evolve.
All right. Oh, let me. And we're going to see a little bit more. I think this is using the future when you're doing training.
So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom.
Sorry, just to be clear here, he's talking. I get confused. There's so many different clips that I looked at. What he's talking about here is they've made a lot of progress. They're doing really good. This is the clip on the right here is something I don't think I bothered showing you because it's hard to explain. But he's just talking about how well the system is working now. But they're still looking to do better in the future. They're looking for better algorithms, better ways of doing things. And latency is a particular issue that you want the chip to make decisions really, really fast. And latency, the more latency you have, the slower the chip makes decisions. So, what can they do to improve latency so that it makes decisions quicker? That's just an example, but there's more here. Let's see.
Or for example, our outputs are dense rasters. And it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements. So this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing.
So the point is, they're not done. Again, this is a recruiting exercise. We're not done. We're still working on it, and it's something that I think they probably should have said it more during the event. But here's all the things we're working on. We need people to help us do this. Makes perfect sense to me. All right, so I think we're now ready to move on to what are we moving on to? Moving on to shrinking me down for one thing. I don't need to be this big. But remember, insanely gigantic boggles the mind, really. One of the most valuable things ever done in the history of civilization. And get the stainless steel mug, all on elonbits.com. Let me, all right, I'm going to move myself out of the way as much as possible. Probably move myself smaller. So what do we have next? We have, I don't think we did Ashok yet. Okay, so Ashok auto labeling. All right, let's do Ashok.
So a single car driving through.
Ashok is another key member of the Tesla team, and myself down and move myself over here. All right, let's see what Ashok is working on auto labeling. This is how the Tesla neural network training computer is able to cover manual labeling. I think maybe I didn't cover manual labeling. Wait, let me just check here. I don't think I covered manual labeling. Let's go back. I think I need to cover manual labeling first. Okay. I got to do this first, and then we'll get back to...
Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so
you haven't figured it out yet. I don't know what I'm doing.
Imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are...
Okay.
Now...
Shrink myself down here. Okay, so Karpathy is going to explain the manual labeling problem, and this is going to show why it's really important to go to auto labeling, which is the next thing.
Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it.
They've got to label the lines on the road. They've got to label the cones. They've got to label the traffic lights. They've got to label the trucks and cars, and maybe they have to label the trees, and they have to label the guardrails and the curbs. There's all these different things that have to be labeled. And if you have to have humans label every single, and I think there's a guy standing on the road with a stop sign. If you have to have humans label every single object, it's going to take forever. You'll never get done with the job. So there's more. So he's going to show
So
this
very
a little
quickly,
bit.
we graduated to 3-dimensional or 4-dimensional labeling.
So that was the early labeling where they were labeling on a single frame at a time, and now I've talked before about you have single versus multi. So they stitch together multiple images so that the labeler is looking at a 3-dimensional space along with the images, and they're able to label objects in 3 space. So instead of labeling on 8 separate images one moment at a time, they're able to label all the video together over a period of time, and it makes the human labelers much faster. So you can see at the bottom, it says 100x labeling throughput. By making this change, humans were able to label 100 times faster, which still helps, but it's not enough, and that's why we're going to auto labeling.
We are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels, because you label once in 3D, and then you get to reproject. But even this, we realized, was actually not going to cut it. Because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're going to now talk about auto labeling, which is some of the infrastructure we've developed for
auto labeling. So even though they made humans 100 times faster by doing what they did, it's not fast enough, and they need to go faster.
So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations.
Let me go back to the beginning of this clip. So the first thing is that the car is driving along, and it is on its own identifying
this
lane
produces an
lines.
effective way. So a single car driving through some location can sweep out some patch around the trajectory using this technique.
So they've developed a technique where the car alone can identify lane lines and other objects as it drives along. And as the car does this, it's generating this picture, and then what you're going to see is they can then take the same thing from multiple cars.
But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations.
So now all of this has been put together by the computer. So this is a job that Karpathy was just showing you humans were doing, and they were doing it 100 times faster than they were doing before, but still slower. And now they're able to use the data from the cars, put it into the training supercomputer, and the training clusters are able to identify these things from one vehicle, and then they're able to merge it together with multiple vehicles, and then
together this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. Again, the point of this is not to just build HT maps or anything like that. It's only to label the clips through these intersections. So we don't have to maintain them forever, as long as the labels are consistent with the videos that they were collected at. Optionally, then humans can come on top of this and clean up any noise or add additional metadata to make it even richer.
So there's still a role for humans. The computers generate, the neural network training figures out from the data how the chips in the car should identify where the lanes are. And they use all the information they get, not only from that car, but from other cars that have driven through the same place, to do a better job of identifying what's a lane line, what are all these objects, and then humans can come in on top after the computers have done all that work. They've replaced, 100 labelers. They've been able to do the same work of 100 labels in a year. The computers were able to do that in a day. And then a human label can come in on top and say, is there anything else that needs to be annotated? Any other data on this thing that the car should have recognized that maybe if we train it, it can recognize that better, and that'll be useful.
We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras.
3D point cloud. Now, when you ever hear somebody talk about LiDAR and how you need LiDAR, what LiDAR delivers to the car is a point cloud. What you're seeing at the bottom here is a point cloud. This is a computer representation of basically where every pixel is in a 3D space. And you can see the purple is the road surface and the white are walls but here's the key point is that the key point for me is it's able to generate this point cloud without LiDAR, which LiDAR is expensive, LiDAR is bulky, LiDAR is ugly. There's a lot of problems with LiDAR. LiDAR might not last as long. Cameras are cheap. This is a much better way of doing things.
The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see on the scene.
So now the computer is able to label objects, and then humans are able to, if there's a problem and the computer isn't able to label objects, a human may be able to come in and label an object that the computer couldn't label. And all of this labeling helps the vehicle understand, helps FSD understand the world around it, will help TeslaBot understand the world around it. And this is a key part of what we're doing here. Okay, so that was auto labeling number one. There's a lot of we're doing a lot of auto labeling coming up. The snow is coming soon too. But there's more auto labeling here.
One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say in the...
Oh, I love this one. So watch this clip and watch, there's little lines in front of the pedestrians. And what's going on here is because you're at the training level, like the car can't see the future, but the car records video. And if the training, let me put myself on the screen, sorry. The car can't see the future, right? But when you're taking the video that the car generated and you send it up to the training computer, and the training computer is trying to figure out what the car should have predicted, the training computer can see the future in the process of trying to learn from the scene. So this is what the training computer can see, including the lines indicating where the pedestrians are going, and that helps them learn. Hope that made sense. All right, let's listen to Ashok.
One more cool advantage of doing all of this on the servers offline is that we have...
You can see this yellow person with a hood on is walking, and then the screen in front of... let me get my left arrow up. See if I can get my left arrow up. Okay. Here's the car that's driving. You can see this yellow person here and wearing a hood, and that's this yellow person here. And you can see the line project out in front. That's the neural network training computer knows where he's going. Here's the blue guy, and you can see the blue guy on the road. And here's the green car, and you can see the green car. And on the side camera, you can see this yellow car. The car is not actually yellow. It's just using yellow to indicate the person. You can see the orange person here, and you can see the orange person's line. So it's using information about the future to train the neural network about how to learn. This is like mind-blowing. Let me try it again. Sorry.
One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics like velocity, acceleration, etc. One more advantage is that we can have like different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them.
Occlusions. Occlusions are when you can see, let me pop this baby back up. You can see here, do that to me. You can see here, so the green car is blocking the view of these pedestrians back here. They're occluded. You can see this pedestrian here is occluded by the orange car, right? You've got the orange vehicle here, and you've got this pedestrian back here, but the car can still see them. Not that they can actually see them, but they know that they're there. The memory is persisted, and in particular, the neural network training computer has the past video and future video, and knows where he was before and where he's going to be later. And so even though there's an occlusion, it can anticipate this is where he is, this is where he was going. So it can sort of follow where that person's going. It can see through cars, right? It can see through objects, not really see through, but it can anticipate well enough to make really, really good predictions. Let me go back again. Sorry, I'm cutting it. I probably shouldn't be interrupting, but
Okay, that even through occlusions, because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars.
the pedestrians on the opposite side of the road are persistent through multiple occlusions. You can see it again here. You can see it again here. The car is occluding these pedestrians. The car is occluding these pedestrians here, but you can still see them because it has the benefit of hindsight, and it remembers what happened before, and it knows what's going to happen in the future. This is a neural network training computer because it's using video that already happened. So it's able to use that to train the hardware to do a better job.
This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they're occluded. So this is a massive advantage.
Okay, planner, we're coming to planning in a minute. Not in a minute, probably in a few minutes, but we're going to do a little bit more labeling, and then we're going to get to planning. And the planning part is also really cool. All right, so let me get rid of this. Let me bring up next auto labeling clip.
We can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects, even through occlusions.
Okay, hang on a second. Okay, let's fire this baby up. This is Ashok talking about auto labeling again.
We can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects.
So okay, so you've got a camera on the left. This is the left rear camera. The left side of the camera looking back to the rear. This is the left side camera looking to the left and maybe a little front. This is one of the cameras on the front looking towards the front and left. This is the central front camera. You've got all these different cameras that are looking at different angles. And this in the middle here, this is a 3D representation, essentially a vector space or a simulation. This is how the car can see the whole world based on all these cameras, all the cameras stitched up. And this is going to play into simulation later. Let me keep going with this clip.
Even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us.
So, this is about labeling. This is identifying objects, predicting what the attributes of the objects, where are they moving, how big are they, what kind of object is it, does this object have properties that are important, like a stop sign, is that a parked car, is that a moving car, that, a lot of different things like that.
This is one more example of the same thing. You can see how everything is consistent. We want to produce 1 million such labeled clips, then train our multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that you're seeing here in the car. Everything together.
We want to get the same view. Sorry. They want to get the same, they want the car. This is what the training computer is using to see and to label objects. And they want to get to the point where they can use 1 million clips like this to train the chip in the car so that the car sees the world like this and identifies objects in this way. Really, really big stuff. All right, let's see what else we got. Got more clips coming. What's everybody doing? All right, let's see. That was okay. So now we're going to do snow occlusion.
We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early
Okay, now we're going to do snow occlusion. So this clip is, I believe this is what it looked like before they had it fixed, and then the next clip is what it looked like after they fixed it. So this is when they were using radar and vision and single frames together, and it does not do a very good job.
We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because.
So what we're seeing here. Oh, I wanted. Come on. Okay, so this is the video of what's actually happening. And then over here, you've got this truck coming, and the truck is going to kick up a bunch of snow or dump a bunch of snow off, and it's going to obscure the camera's view of the vehicles ahead of the car and the lane lines. And what you're going to see is that the lane lines are going to get all jiggy, and it's going to have trouble tracking these vehicles once that happens. Let's go try it again.
We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us, and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because of the lack of data in such conditions. So what we did, we asked the fleet to produce lots of similar clips, and the fleet responded, it did.
This is one of those things that Karpathy talked about before. They can query the fleet. We've encountered something we're having difficulty with. Let's ask the fleet of the cars, do you have something like this? And you can see up here, he's going to talk about it. They generated 10,000 similar clips that they were able to collect and automatically label in 1 week. There's no way you could do that with humans. This is why auto labeling is so important, and it's why having the fleet is so important. You have a fleet of 1 million plus cars, and you need data of a certain kind, and you go out to the fleet and say, hey, do you have anything like this? And 1/100th of the cars have clips like that in the past week. Well, that's 10,000 cars. And if you go up to a bigger fleet, you're going to have more clips like this.
It produces lots of video clips where shit's falling out of all other vehicles. And we sent this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this.
So they're solving problems by having large data sets because they have all these cars out there. They're able to query the fleet and say, hey, do you have something like this? And somehow they're able to communicate to the cars, this is the kind of situation we're looking for. The cars are able to send back, I have data like that. And then they're able to train, they're able to auto-label because they've got these auto-labeling algorithms and they've developed their systems to be able to do it. And then they're able to train based on what they learned from that. Stunning what they're doing here. All right, there's another occlusion one, I think. See what I got
so once
here.
we train the networks with this data,
this is,
you
I
can
think,
see
what
that
happens
it's totally working and keeps in memory that this object was there and provides this.
All right, this is what's going to happen. Then this is after they've made this improvement. After they made this improvement, check how much better it works.
So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this. So once we train the
So you can see on the left is what we saw before, and on the right is how it looks now. And you can see these boxes around the vehicles in front, and they stay persistent. They don't go all jiggy.
Networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this.
So the point is, they're doing all this, and there's a reason they're putting all this work in. They're able to identify objects and track objects and anticipate where objects are going to be and predict where objects are going to be, and they're able to do much better. And this is all going to lead to better prediction down the road. So let's do planning. I think this is what I wanted to do
We're
next.
trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this,
Okay, I think I'm just going to let Ashok talk, but planning a lane change. This is actually, I think this is a really interesting clip. So car's in the right lane. Car has to make a double lane change to get over to make a left turn, and there's traffic. How does it do it? I'm probably going to go through this clip a couple times.
we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over.
Let me just pop up my arrow here. Okay, so this is ego. This is the car that's driving. It needs to get over here to make a left turn. So it needs to make a left lane change here. It needs to make a left lane change here. And there's a car in the way. And there's a car behind. And there's cars. How is it going to pull off this double lane change to get over to make its left turn? And that's the challenge. Just should be clear, but in case it's not clear, I just wanted to cover that. All right, let's go ahead.
Different maneuvers. So in the first one, it searches is a lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span, because these are all physics-based.
This is trying to figure out how am I going to make this double lane change, and it basically simulates 2,500 different ways of trying to do the lane change and figure out which ones are the safest, which ones are the best ways of doing it.
Models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan.
So I think I'm actually blocking the, let me play this clip again. I think I'm actually blocking the view. He's talking about these, these graphs here. So let me take the arrow off and let me play that clip again. And I'm actually not clear whether he's talking about this calculation being done by the chip in the car, or if this is the training going on, the training computer figuring out, okay, this is a scenario, how do we train the car to handle this? The way I heard this, the car is actually, as it's driving along, it's looking at 2,500 different ways it might make the next move, and then deciding which one to do based on that, and it's all making those calculations in milliseconds.
So we are able to plan for 10 seconds here and able to match that when we see.
Go back to the beginning, sorry.
We're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead.
It's actually a triple lane change if you watch it.
For this, the car searches over different maneuvers. So in the first one, it searches is a lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan.
So I believe he's talking about the stuff on the side here. Let me pop that back up. I believe he's talking about this. I believe he's talking about this. This is where it's trying to go. It's closely tracking where it's trying to go, and this is the velocity. So it's mostly tracking the velocity that it had planned. That's what I think he's talking about. There's more coming on this. on planning. Let me, we done with that? I think there's a little more
So
here.
we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan.
So that their car is actually able to plan 10 seconds ahead, at least, and what the example he's showing here. So let's go with, I think this is the next one I wanted to show.
It's important to not just plan for ourselves.
Oh, yeah. This
but
is
instead,
really
we have
good.
to plan for everyone jointly and optimize for
Give
the
me a
overall
second.
scene's
This is really
traffic
good. This
flow.
is good stuff.
In order to do this, what we do is we literally run.
Okay, let's check. This is cool.
It's important to not just plan for ourselves, but instead, we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene.
They run the planner. What you just saw, planning how the car is going to move and figuring a bunch of different options and which one's the best option. It does the same thing for every moving object, figuring out 2,500 different ways that might move, 2,500, and tries to figure out what are the most likely ways that thing is going to move, so it can plan how it moves in anticipation of how the other thing's going to move.
Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side, but the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the park.
Let me just hit that again. This other car comes up
here. Autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner.
You can see here on the right side, you can see oncoming cars prediction to go around other parked cars, high probability. Oncoming cars prediction to yield, low probability. So the car is predicting there's two general possibilities of what that car is going to do. It might come through and I have to get out of the way, or it might yield and then I can go through. And at the initial moment that car's coming, it looks like it's coming fast, and the car decides, you know what, I better be careful. I think that car might come through.
For the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, okay, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues.
So you can see the car figures it out. You know, when the other car changes its behavior, autopilot updates its projection of what that car is going to do, realizes that car has decided to yield, and then it proceeds forward. And we all do this in our own driving, but it's actually pulling off these very complex driving maneuvers. Really, really cool that it's doing that. Okay, so changes. And I wanted to include this bit here because I think this is, I'm really pleased with myself. I got something right again.
Convex corridor.
So that's
and
why
we
I'm
initialize
showing
the
this.
spline and heading and acceleration parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example.
Okay, so I put myself. I think I'm going to hide myself on this one. So I'm going to put the arrow up. You got the arrow here. So you've got the car is approaching what it's doing. You have this, what's really interesting to me here is you've got this cost function, you've got this traversal time, you've got collision risk, you've got lateral acceleration, you've got lateral jerk. The car is looking at all of these different characteristics to decide what's important here. Collision risk, you want collision risk to always be very low. And this is actually, when I interviewed James Dauma, I had this theory that the car is measuring collision risk right here. This is the collision risk graph. You can see the word, if you can look closer, you zoom in or whatever, you can see this says collision risk here. This is a graph. It is trying to minimize collision risk. It is also trying to, minimize the time it takes to get where it's going. It is also trying to reduce cost. There's an overall cost function, which is a combination of all these other things and more. It's trying to keep lateral acceleration and lateral jerk down because lateral acceleration and lateral jerk makes the ride less comfortable. You want a more comfortable ride. So if the car drives in a jerky manner, then that's not pleasant for the person in the car. There's all these different things that you're trying to figure out. How do we keep all these things ideal so that the person in the car enjoys the ride, and doesn't crash, right? The number one thing is don't crash. And you can see probability of crash is really, really low. That's like a huge, huge feature that they're focusing on. All right, let's go back to, let's let Ashok talk.
Here, the gray thing is the convex corridor, and we initialize the spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, here on the right side, the green plot. That's a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it looked like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. Here.
All right, so that was that one, and then I'm gone. Okay. Just to be clear, we're talking about the planning function. There's perception and there's planning and there's execution. As far as I know, execution was not really covered much in this talk. But right now, execution is done not by machine learning, but eventually execution, as in how hard to the actual carrying out of the acceleration, the turns, whatever. That may still be done by hand-coded stuff, but eventually that'll be taken over by machine learning as well. But we've been talking about the perception stuff before with Karpathy. Now we're talking about the planning stuff with Ashok, and labeling helps identify objects and then is used for the planning. Let's see what else we got. We got a couple things in a parking lot here.
Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange.
Okay, so here we've got cars here, and the car wants to park here, and they've set up this difficult parking problem where you've got all these cars and you've got these cones, and it's not supposed to hit the cones of the cars. It's supposed to come around here and manage to park in the spot. And so they had different models for how to do this, and you're going to see the first model is terrible, and it gets better over time, and then we're going to see different models do better.
Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. So this is a simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search. And the heuristic here is the distance, the Euclidean distance to the goal.
Eugene, thanks for your support.
So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this.
So really quick here, if you look down here, you can see there were 400,000 different paths that it searched before it figured out how to make this parking maneuver. And that's not efficient. That's going to take a really long time. It's a really excessive use of compute. So can we find better ways of doing this is the challenge. So keep going.
Obviously, this is a terrible heuristic. We want to do better than this. So if you added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's in collision, and if it's in collision, back up. The navigation heuristic helped, but still, this took 22,000 nodes.
So again, you can see it took a long time to make its decisions. It took 22,000 searches, which again, is a lot of compute. It's very inefficient and it makes it run very poorly. So let's try. Let's go. Now we got to move on. I got to bring the next one up. This is where
See how
it gets
MCTS
fun.
tree search does.
And let's see.
Here you notice that.
Okay, so same parking lot. Now let's see with the better model.
The planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. See how MCTS tree search does. Here you notice that
what you can see here, you've got this, it's sending this tether out, which should look familiar to FSD beta testers. And you can see right at the end, it's searching different ways it might carry out the task, but only at the end of the tether rather than looking at a much more complicated set of problems.
Planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible.
So the key detail here is it only used 288 searches instead of 400,000 searches or 22,000 searches, which means it's much better computing to get to its goal. So this is and you can see it over here in the search space. With one algorithm, it took 400,000 expansions. With the new algorithm using navigation, Euclidean plus navigation was 22,000, and then using neural network policy and value function, a very different, radically different algorithm. They were end up able to do it with 288 searches, so much quicker. So the neural network approach to the parking problem was much better. Okay, I think that's all we have from Ashok. We're going to move on. Hello. Hope you're all doing well. Boy, we've been going a long time. How are we doing here? With 2 hours and 22 minutes so far. 2 hours, probably 2 hours and 10 minutes so far. Let's see if we can keep this going. All right. Let me see what we got next. We did Ashok, we did Karpathy. So now we're going to go to simulation. Okay. We're going back to Ashok on the simulation side of things. And all right, and let me self small and out of the way. Okay, so we're on a Ashok simulation. So we're moving on from the snow occlusion.
So finally, we wanted to actually get a Cybertruck into a data set for the remove the radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty. It looks very pretty.
Let's watch that again. Okay. I think they just did this for fun. They wanted to try this with a Cybertruck and having autopilot running through a Cybertruck.
Finally, we wanted to actually get a Cybertruck into a data set for the remove the radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation.
This is a photorealistic simulation. When I first saw this clip, I just assumed that was a Cybertruck on the road. Look at the pavement. look at the crosswalk and the lines in the crosswalk. Look at the vehicles. If you look really close at the vehicles in later versions of this, you're going to see pedestrians. Once you see the pedestrians moving, it's a little more obvious that it's a simulation, but this is how photorealistic they are using simulations. Kind of interesting that there's this perspective that simulation is unnecessary or not useful. I've just watched Ishan Misra was interviewed by Lex Friedman. They were talking about simulations not useful. There are reasons why they need good simulations, which is going to come up later in this live stream. I'm going to talk about why it's necessary. We're going to hear Elon, I think, talk about why it's necessary. But they have decided, and for reasons that we'll see later, they have decided they need really good simulations to be able to test scenarios. If you want to test high risk of crash scenarios, it's a lot better to test it in simulation than test it on the road. That's the basic point. And if you want to test rare scenarios, things that like the real edge cases that are very rare to happen, it's very hard to get good data. So you can recreate once you have an edge case, you can recreate similar edge cases in the simulation. That's the basic idea. So let's go to.
So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data.
All right, so this is the same scene, and this is the same scene. Let's go ahead with it.
So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data. So this is the
So they use simulation to label data. It's not just for dealing with how to encounter things, but also how do you label things in the roadway. And if you have simulations, you can train your labeling, and you can generate a lot more data to do labeling.
same scene as seen before, but from a different camera angle.
You can see the Cybertruck is here from the same we're just a different camera angle. Before we were looking this way from the car. Now you can see the Cybertruck is here. You can see that big truck is here, and here's Ego Car. This is the car that's driving. That's trying to figure everything out.
So a few things that I wanted to point out. For example, the ground surface. It's not plain asphalt. There are lots of cars and cracks and tar seams. There's some patchwork done on top of it. Vehicles move realistically. The truck is articulated, even goes over the curb and makes a wide turn. The other cars behave smartly. They avoid collisions, go around cars, and also smooth and accelerate smoothly, brake and accelerate smoothly. The car here with the logo on the top is Autopilot. Actually, Autopilot is driving that car, and it's making unprotected left turn. And since this is a simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly.
So a critical detail there that he said right at the end was one of the things they use the simulations for is when Andre is the head of the vision team, says, hey, we need to be able to do this and we need to be able to test this. They can create simulations that allow them to test whatever it is that Andre wanted to test. And because they have this really robust simulation software and I guess hardware to go along with it, they're able to generate simulations really quickly. And there's a lot more about simulations coming. This is not the simulation hypothesis, by the way.
Render the
But the
second, we need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of pains to produce nice spatiotemporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic.
The simulation doesn't help with auto labeling if the simulation isn't photorealistic. If it doesn't look like the road looks to the cameras on the car, which is something that we're going to cover more about in a minute, by making the simulation as photorealistic as possible, it is faithful to what the car will see in the real world as much as possible.
Yeah, in addition, we also use ray tracing to produce realistic lighting and global illumination. OK, that's the last of the cop cars, I think.
So you need photorealistic rendering, and you need like the lighting to be accurate so that the car sees if the simulation doesn't look the same to the car as the real world, then your efforts to label and your efforts to learn how to drive in a simulation might not translate well to the real world. That's a big concern. All right, let's go on.
Of data for the network.
Okay.
For the network. But a lot of this data can be boring because the network may not already get it correct. So what we do is we use also ML-based techniques to basically perturb the network to see where it's failing at and create more data around the failure points of the network. So this is in closed loop trying to make the network performance be better. We don't want to stop there. So actually, we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on.
Recreate any failures in simulation. So if something goes wrong in the real world or in simulation, I think if something goes wrong in the real world, you can see on the left side is a real world clip. If something goes wrong, if it does something badly, then you want to recreate that in simulation, and then you can you can simulate what happened in many different ways, many variations of what happened to see if you can train the vehicle to do better through the simulation. Sorry.
So here on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects. With this combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of it. And then when we replay autopilot on it, autopilot can do entirely new things, and we can form new worlds, new outcomes from the original failure. This is amazing because we really don't want autopilot to fail, and when it fails, we want to capture it and keep it to that bar.
I'm just showing you step by step through how they're using simulations and how they're generating the simulation. So they're taking real world, they're auto labeling the real world, and then they take the real world data to create a simulated version of that real world that they can then run a bunch of simulations on. Let's see, we got one more here from Ashok's
Not just that,
talk.
we can actually take the same.
Sometimes I think I should have just run longer clips. This is hard. All right, let's go.
We can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras. This is a result from last night because it was cool and we wanted to present it. But yeah, I'm very excited for what Sim can achieve.
So let's go through that again. So
Not just that.
This is what it looks like through the simulation with this additional feature they've added called neural rendering.
We can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic.
Right now, this is original. This is actually an original video clip, and that guy on the left is a real person, and everything you're seeing is real.
We take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras.
And what he was excited about was they're still working on this stuff. Again, this is a call to engineers. We want you. This is a new approach to doing this, and it's results from last night. This is something they just did last night, or the night before, actually, because 2 days ago for me, a day ago for them. They are still excited about the developments that they're making, the improvements they're making as they go along. Okay, so I want to switch to the Q&A now. Let's see. So Elon was asked about the use of simulation.
The simulator...
Pause this.
The simulator is very helpful when there's like these rare cases, like like collision avoidance right before an accident. And then, ironically, the better our cars become at avoiding accidents, the fewer accidents there are, so then our training set is small, so then we have to make them crash in the simulation. So it's like, okay, minimize potential injury to pedestrians and people in the car. You have 5 meters, you're traveling at 20 meters per second. What actions would minimize probability of injury? We can run that in sim. So.
Again, that's the key point, that as FSD gets better and better, crash situations will become more rare. So it's harder to train when you have less data. If the problem that you're concerned about becomes more and more rare, it's harder and harder to train on it. So when you have something bad happen, you can't query the fleet anymore to find similar situations because the car's gotten so good it's avoiding crashes more. So you can take that situation and you can put it into simulation, and you can replicate it in a bunch of different ways. You can create a bunch of different versions of the same scenario with human help to decide, or how are we going to do this? Or maybe you can use computers to generate a whole bunch of different scenarios and run it through that way, and then train it to minimize crash. Minimize crash, minimize risk of injury, minimize risk of serious injury. These are goals that they have. So that was one bit. Here's the next one.
Overwhelmingly,
He's asked about
the data
this multiple
set
times.
The data set is the real video from the cars on the actual roads. Nothing's weirder or has more corner cases than reality. It gets really strange out there. But then if we find, say, a few examples of something very odd, and there's some very odd pictures we've seen, then in order to train it effectively, we want to create simulations, say 1,000 simulations that are variants of that quirky thing that we saw, to fill in some important gaps and make the system better. And really, all of this is about, over time, just reducing the probability of a crash or an injury, and it's called the march of nines. Like, how do you get to 99.9999999% safe? And each 9 is an order of magnitude difficulty.
Each 9 is an order of magnitude harder. So, the goal here is to make it as safe as possible. Given that you have some other constraints, like you need to get from point A to point, the safest as possible when we don't move the car, but you need to get from point A to point B. So they're constantly working to say, how do we minimize the risk of crash? How do we minimize the risk of injury? And when, like I just said before, when Elon's talking about, when you get to crashes are rare, then you can generate similar situations, 1,000 versions of it in simulation, and you can train on that. That's pretty cool. And then what's the last one I have? Oh, I think there was a question related to the simulation, and somehow it led into the TeslaBot. So let me freeze here.
So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So we want to expand eventually to being a universal simulation platform. But I think before that, we're going to be spinning up a lot of Optimus support. And then a little bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
Optimus is the code name for the TeslaBot.
Oops.
Optimus subprime.
I think I'm going to play that clip again. So there was a question about how simulation is going to be used, and this is the guy who's basically in charge of simulations, as best I can tell, or one of the guys who's in charge of simulations for the company. Forgot his name, but let's play this clip again.
So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to
BMS is battery management system. MCU is I believe that's the unit that's inside the car that controls multimedia entertainment. I don't know why they need to simulate that, but apparently they need to simulate that.
need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So I want to expand, or we want to expand eventually to being a universal simulation platform.
So that one of the things that they're trying to do, this is like a takeaway that probably no one's taken away from this. They're trying to create a universal simulation platform, which would help with AI training for real world for other situations, including.
But I think before that, we're going to be spinning up a lot of Optimus support.
Optimus support. They expect to be using the simulations, the simulation setup to train Optimus. Optimus? That's the first time we've heard Optimus. What's Optimus? And he gave away something he wasn't supposed to give away. A little bit more
a little
here.
bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
So that ultimately they can see offering simulation as a service. We've talked about Dojo as a service. They're actually thinking about offering simulation as a service to others outside the company. This is another business line for Tesla that no one is accounting for. Now, I'm not saying it's going to be a huge business line. It could be a huge business line, and it could go along with Dojo as a service, as something that goes along with it, or it could be used for other purposes. But again, they keep coming up with innovations in the company that are useful within the company that may be useful outside the company to other customers.
Optimus is the code name for the TeslaBot.
Oops.
Optimus subprime.
Sorry, for anybody who's not in on the joke, Optimus Prime is, I believe, a character in the Transformers series. A big scary robot. So this is not Optimus Prime, the big scary robot. Might be the hero. I'm not that familiar with Transformers, but a big scary powerful robot. This is not a big scary powerful robot. So Elon's jokingly calling it Optimus Subprime. All right, so let me go to, what do we got next? All right, full self-driving. This is going to be a big chunk on full self-driving. What do we got on full self-driving? There's a lot on full self-driving. This is all quite Q&A stuff that related to full self-driving. There wasn't a specific, we've seen a lot of stuff with full self-driving, but this is specific stuff. So let's see a couple of details. I'm trying to decide what I want to do first. I guess this is closest to what we've been talking about so far.
I think one of the things we're seeing is that the car's predictive ability is eerily good. It's really getting better than human in terms of predicting, like you said, predict what this road will look like when it's out of sight, like it's around the bend, and it predicts the road with very high accuracy, predict pedestrians or cyclists where behind, where it just sees a little corner of the bicycle and a little bit through the windows of the bus. And its ability to predict things is going to be much better than humans, like really way beyond.
Right. Yeah, we see this often.
Talking about predicting, what I was showing earlier in the video is how the neural net is able to predict, is able to see where humans are who are occluded, right? You saw a pedestrian and then a car drove in front and you can't see the pedestrian more, but the neural network is able to remember that's where the person was before. This is the direction they were going. This is probably where he is. And it's able to predict things in the roadway better than humans are able to predict things. And this is why Elon believes and the team believes that it's going to get better than human as a driver very soon.
We have something that is not visible, but the neural network is making up stuff that actually is very sensible. Sometimes it's eerily good, and you have to you're wondering this is in the training set. And actually in the limit, you can imagine the neural net has enough parameters to potentially remember Earth.
What? This is the line that got me. I didn't understand. I still don't. I'm not exactly sure I understand what Karpathy just said there, what Andrej Karpathy just said here. The neural network has enough parameters to remember the Earth. I don't know if he means that. This is one of those, like, what the hell did he just say? I don't know what he just said. What the hell was that? I don't understand.
So in the limit, it could actually give you the correct answer, and it's kind of like an HD map baked into the weights of the neural net.
That is some freaky stuff there. I'm not claiming I understand what he means. That is freaky deaky stuff. This was a question about.
Well, driving is fundamentally.
Hang on, This was a question about multimodalities. This is a popular topic. I just watched Ishran Misra talk about this in his interview with Lex Friedman. Stuff over here, but
well, driving is fundamentally basically almost entirely vision neural nets. It's running on a biological vision neural net, and what we're doing here is a silicon camera neural net. So there is some amount of audio. You want to hear if there's like emergency vehicles or I guess converse with the people in the car. If somebody's yelling something at the car, the car needs to understand what that is. All the things that are necessary for it to be fully autonomous. Yeah.
So there was just an interview. I think I mentioned this earlier in this. There was an interview about 3 weeks ago, 3 weeks ago, with Lex Friedman interviewed Ishran Misra. Ishran Misra is like director of AI for Facebook, or one of the big guys at Facebook doing AI there. And there was this part of the conversation was multimodality. So you've got vision and you've got other sensors. So, in the past, they've tried to fuse radar and vision. They've tried to fuse light. Some people are trying to use LiDAR and radar and vision. And, is it helpful to have other different sensors, other different ways of detecting the world when you're trying to put things together? And Elon is saying, no, listen, driving is essentially vision-based, but audio may be helpful in some situations. I don't think they're incorporating audio in FSD yet, but I think that's something that's going to be coming. Obviously, if somebody in the car tells the car to do something, then the car may need to listen to that. If it hears a big noise out on the roadway, and what Mishra talked about was you're looking at a video and somebody's strumming a guitar and you have a guitar sound. Over time, the AI learns that the sound of the guitar is probably coming from the guitar. If you show it enough clips of people playing guitars and guitar music going, it may start identifying that. And so the same thing could apply, I think. I think that's the deeper idea that was in the question that Elon kind of touched on. But Elon's kind of push was sound doesn't matter a whole lot. We're going to have to get there, but that's not a critical detail. And, let's face it, deaf people drive, right? Deaf people drive cars. So people with one eye drive cars. So having 8 cameras, having some audio ability is great, but just being able to see and identify objects is a really, really large part of the game. Okay, so what do we got next? I thought this was a really good one. I'm going through these kind of hodgepodge.
I think I know the literature that you're referring to. That's not some of the problems that we've seen, and we haven't done too much continuous learning.
But I can't, so I
we
gotta
trained the
fix
system
it.
once. We fine-tuned a few times.
Okay, so this is about continuous learning. There was this. This has to do with continuous learning. There was this question that I see as related to the question of whether the car learns while it's driving. The answer to that question is no. But that was the question. Are they applying continuous learning approaches?
I think I know the literature that you're referring to. That's not some of the problems that we've seen, and we haven't done too much continuous learning. We trained the system once. We fine-tuned a few times. That sort of goes into the car. We need something stable that we can evaluate extensively, and then we think that that's good, and that goes into cars. So we don't do too much learning on spot or continuous learning, and don't face the forgetting problem.
I just want to address this real quick. It is a very common perception of some people who drive FSD or who watch FSD videos, and there are some videos that seem to show this, that a car is having trouble doing a particular task, making a right turn in an awkward situation or construction comes or whatever, and the guy intervenes, drives around the block, does it again, intervenes, drives around the block, does it again, and like the third time the car gets it right, and the perception of the FSD, the driver of the car and people watching the video is the car learned. No, it doesn't. The car doesn't learn from its own driving. The car learns from the AI training supercomputer telling it to adjust its weights, and that basically teaches it how to handle new situations. I think that's related to what we're talking about here. But anyway, Elon has more to say.
But there will be settings that you can say, like, if you are you typically a conservative driver, or do you want to drive fast or slow? You know, it's like I'm late for the airport. Could you go faster than, you know, basically the kind of instructions you'd give to your Uber driver. It's like, I'm late for the flight, please hurry, or take it easy, or whatever your style is.
But that's not continuous learning. I don't think Elon was really responsive to the question here, but he is saying the car will be adjustable. So if you wanted to drive more aggressively, you can tell it to drive more aggressively. You wanted to drive, it's probably going to be default set to chill, right? Drive ultra careful and not aggressively. But if you ask it to drive more aggressively and faster, then it will be capable of that. It's not really connected to the question, but that is a feature that he expects to implement in FSD at some point in the future. Just like we already have, the car already has chill mode for, saving battery and or driving aggressively, whatever. That's an option there. Okay, so let's see. Did hearing, did neural net prediction. This is a very common question about countries.
How does the transfer to different countries?
Well, we actually do train on using data from probably like 50 different countries, but we have to pick. As we're trying to advance full self-driving, we need to pick one country, and since we're located here, we pick the U.S. And then we get a lot of questions like, why not even Canada? I'm like, well, because the roads are a little different in Canada, different enough. And so when trying to solve a hard problem, you want to say like, okay, let's not add additional complexity right now. Let's just solve it for the U.S. and then we'll extrapolate to the rest of the world. But we do use video from all around the world.
So this is a very common complaint I hear from Canadians. I have a lot of Canadian friends on Clubhouse and Twitter who are always wondering, when is FSD beta coming to Canada? And I think the answer we just got is not soon. That they're trying to solve the full self-driving problem. And he says, we're here in the US. Well, most of the cars are in the US. The US is the location where most Teslas are being driven. So they are getting data from other countries, and you're going to hear from Andre now that data from other countries is useful, and he doesn't think the problem of extending full self-driving to other countries is going to be that challenging. Listen to Andre.
I think a lot of what we are building is very country agnostic. Fundamentally, all the computer vision components and so on don't care too much about country-specific sort of features. Different countries have roads, and they have curbs, and they have cars, and everything we're building is fairly general for that.
Yeah, and then the prime directive is don't crash.
Right, and that's true for every country.
Yes, this is the prime directive. Even right now, the car is pretty good at not crashing. And so just basically, whatever it is, don't hit it. Even if it's a UFO that crash landed on the highway, and still don't hit it. You should not need to recognize it in order to not hit it. So that's very important.
Elon's big on the not crashing thing. That's an important detail. All right, this was a really, I think the answer to this question was pretty interesting. And
well, with hardware 4, we will have.
There was a question about cameras, whether they're going to be using. The question started off with the idea. This question started off with the idea that the cameras that are existing on the car aren't that good, and the human eye is better, and are they going to be deploying better cameras to make up for the failings of the existing cameras? And Elon kind of tosses that idea, but here, just listen to what he says here.
Flexible camera design, or building your own camera, for example.
Well, with hardware 4, we will have a next generation camera.
So first of all, they're talking about hardware 4, which is the next generation chip that's going to be going in the car and in another car, which you're going to hear in a second, in a future vehicle that we're all excited about. And there will be next generation cameras to go along with the next generation chip.
But I have to say that the current cameras, we have not reached the limit of the current cameras. And I'm confident we can achieve full self-driving with much higher safety than humans with the current cameras and current compute hardware.
There's a constant concern people have is that the existing chipset or the existing cameras are not good enough. We need something better in order to make full self-driving better. And Elon is saying, no, what we have now, as we're on the path, and this is backed by the rest of the team, what we have now is good enough that we will be better than human fairly soon.
But, you know, it would be good to be 1,000% better rather than 300% better. So we'll see continued evolution on all levels in pursuit of that goal. And I think in the future, people will look back and say, wow, I can't believe we had to drive these cars ourselves. You know, it'll like self-driving cars will just be just a normal, like self-driving elevators.
So Elon goes on a little tear there. One of his common comments about self-driving elevators and the good old days, the guy running the elevator occasionally made a mistake and somebody got cut in half. So, all right, so that's on the same loose topic about equipment. Let me go. This is big for me. This is big. I have an order for 1 or 2. Actually, I have an order for 2. 2 orders for.
Hi. With the over here.
We're talking about hardware 4 again.
3, there's been lots of speculation that with larger nets, it's hitting the limits of what it can provide. How much headroom has the extended compute modes provided, and at what point would hardware 4 be required, if at all?
Well, I'm confident that hardware 3 or the full self-driving computer 1 will be able to achieve full self-driving at a safety level much greater than a human, probably, I don't know, at least.
So, you know, again, to emphasize, the chips that are in the cars now, the cameras that are in the car now are good enough that they do expect to achieve better than human, significantly better than human, much better than human on what they have now.
200 or 300% better than a human. Then obviously there will be a future hardware.
Just notice that Ashok and the team is, no one is on the team is saying, wait a minute, no, it's not going to be that good. And it comes up a couple times that he looks at them and they're nodding their heads, they agree. And there are times not just when they're nodding their heads, but they're actively speaking, agreeing and believing that they think they're going to get there. I've seen it from Ashok and I've seen it from Karpathy before, and I haven't seen it from Ashok before. I've seen it from Karpathy before. I saw it from both of them during this presentation. They all believe that they're going to get FSD significantly better than human, 2 or 3 times better than human with the current hardware.
For full self-driving computer 2, which we'll probably introduce with the Cybertruck. So maybe in about a year or so.
So Cybertruck is going to have hardware 4, and this was the death blow for me in about a year or so. Well, let's see, we're in August. I was thinking there was a chance I was going to get my Cybertruck in January to March, and now it looks like the first Cybertrucks might not be available to the 3rd quarter of 2022. I don't know if that's what he meant. I don't know if maybe the first generation of Cybertrucks will have the current hardware 3 chip, and they hope to get the Cybertruck out sooner, but that was not a promising sign for when Cybertruck is going to be available. Maybe he misspoke, maybe that's not what he meant, but they are designing Cybertruck for the next generation hardware, FSD hardware, and the next generation FSD cameras.
That is probably, well, they'll be about 4 times more capable, roughly. But it's really just going to be like, can we take it from, say, for argument's sake, 300% safer than a person to 1,000% safer? Just like there are people on the road who, with varying driving abilities, but we still let people drive.
This is one of my things about full self-driving that I ask people about all the time is, how good does full self-driving have to be? Does it have to be better than the average human? Does it have to be better than the 99th percentile human? And as Elon points out, we still let less than average drivers drive, right? We let the lower end drivers drive, so.
You don't have to be the world's best driver to be on the road. So as we see. So
obviously he's driven in Florida.
Yeah.
So, what else do we have? I don't know if we had this one. I don't think we covered this one yet. This might be the one I was looking for. I got disorganized at the end here. Let's go.
And they don't spin anymore. Not in the. If you've seen the FSD beta videos, they're pretty solid.
This was a question about the quality of how are they going to make people confident that FSD is good enough? And the guy was referring to, the interface on the car when you're looking at the screen and the objects in the screen move around a lot. And Elon is saying, well, if you watched FSD beta, that doesn't happen. The FSD beta videos show a lot of stability in how the images look, and we saw that during the presentation today.
And they will be getting more solid.
Yeah, as you add more and more data and train these multi-cam video networks, like these are pretty recent actually, just like a few months old, and we're still improving it. It's not a done product. And that in our minds, we can clearly see how this is just going to be like perfect vector space, because why not? All the information is there in the videos. It should produce it given lots of data and good architectures.
So there you go. We always hear it from Elon, and this is one of my things about Elon's companies, is when other people on the team are on the same page and not just nodding their heads, but saying the same things. Here's a show saying, we see it getting to perfect, right? Gwynne Shotwell saying, no, we're definitely going to be doing Starship Earth to Earth. When the team is on board with the plan, it's a lot. When Elon just says, oh, we're going to do this, and nobody else is saying it, and maybe they're looking the other way. But when they're affirmatively saying it themselves, this is Ashok putting himself on the line. This isn't just Elon saying it. Now Ashok is saying it, and Karpathy is saying it too. We're going to get there.
And this is just an intermediate point in that timeline.
I mean, it's clearly headed to way better than human, without question.
They're headed to way better than human, without question, on what they have now. Additional hardware is great, but they're headed to way better than human on what they have now. So I think the last clip I have is... This is the last clip I have. And I think I might have two more clips that are outside my fold. Sorry. I might have a couple more clips, and then we're going to talk more. So let me hear what this is. This is about... This is computers are fast and humans are slow.
Well, I mean, the thing to appreciate is that from the computer standpoint, everything is moving slowly. So, to a human, things are moving fast. To the computer, they are not moving fast. So I think this is, in reality, somewhat of a false dichotomy. Not that it will never happen, but it will be very rare. If you think of it like...
I think the question was about what if the computer has to make a split-second decision and doesn't have a lot of time to make the decision. And Elon's point is that that's a big challenge for humans because humans don't think very quickly, and also humans don't process the whole scene all at once. The car is processing the whole scene, all 360 degrees, updating every 50 times a second, 60 times a second, something like that. Humans, we don't process that fast. We can't see the whole scene. And the computer just makes decisions quicker than we do. It's able to make decisions much quicker. And he talks about that. Let me keep going here.
Going the other direction, like rendering, with full ray tracing, neural net enhanced graphics on something like Cyberpunk or any advanced video game, doing 60 frames a second.
This is a brutal death's blow to humans. Humans thinking we're better than computers.
Perfectly rendered. Like, how long would it take a person to even render one frame, and without any mistakes? Can't be done. I mean, it would take like a month just to render one frame out of 60 in a second in a video game.
So computers render 60 frames a second of high resolution imagery, incredibly high resolution, photorealistic imagery, 60 times a second. To do one of those frames would take a human a month, maybe, if they could do it at all. That's how fast computers are and how good computers are at certain things.
It's computers are fast and humans are slow.
Computers are fast.
I mean, for example, on the rocket side, you cannot steer the rocket to orbit. We actually hooked up a joystick to see if anyone could steer the rocket to orbit, but you need to react at roughly 6-7 hertz. People can't do it. Not even
6-7 hertz means you have to react 6 or 7 times a second. You have to make 6 or 7 correct decisions a second, and humans can't do it.
Now that's pretty low, you know. We're talking more like aiming for like 30 hertz type of thing.
The car's making 30 decisions a second. We have trouble making even 6 decisions a second. So the car is able to make decisions much quicker than we are. So the challenge of cars having to make split-second decisions is much less than it is with humans. So I think I might have a couple more clips to throw in here from, that was it, covered Cybertruck. So, all right. Do this question first, and we'll close with a
we've
fun
seen
question.
other We've seen other companies, for example, use reinforcement learning and machine learning to optimize power consumption in data centers and all kinds of other internal processes. My question is Tesla using machine learning within its manufacturing, design, or other engineering processes?
Elon doesn't like this question.
I discourage use of machine learning because it's really difficult. Unless you have to use machine learning, don't do it. It's usually a red flag when somebody says, we want to use machine learning to solve this task. I'm like, that sounds like bullshit. 99.9% of the time, you do not need it. So it's kind of like you reach for machine learning when you need to. No, but I've not found it to be a convenient, easy thing to do. It's a super hard thing to do. Now, that may change if you've got a humanoid robot that can, understand normal instructions. Generally minimize use of machine learning in the factory.
So this is a lot of people think that the TeslaBot is for doing work inside the factory. People think that machine learning, we're doing all this machine learning. Are you applying the machine learning to how you do things in the factory? I've had my theory that they might be using machine learning to design the chassis for the Roadster. And I think this was pretty much a smack in the face to me. No, Warren, we're not using machine learning. Of course, Elon's not thinking of me. But no, they're probably not using machine learning to design the chassis of the Roadster. That in general, if you don't need to use machine learning, don't. It's only when the other methods won't work and machine learning shows promise that you use machine learning, that regular, roll up your sleeves and do the engineering, the hard work, is apparently better in most situations. And there's not an advantage to using machine learning. I think that's pretty clear. All right, so the last clip, this is I would say is
that something that you guys are worried about?
Here. Remember exactly what about artificial general intelligence. So that's why I think it's a good one to close on. Oh, I did that. Okay. Sorry.
You guys deploy more and more robots, or do you guys we'll solve that problem when we get there?
Yeah, I think that we should be worried about AI. Now, what we're trying to do here is, say, narrow AI, or pretty narrow, just make the car drive better than a human, and then have the humanoid robot be able to do basic stuff. So at the point at which you sort of start to get to superhuman intelligence, yeah, I don't know, all bets are off. But and that's quite, that'll probably happen. But what we're trying to do here at Tesla is make useful AI that people love and is unequivocally good. That's our, we'll try to aim for that.
So there's this general principle, I guess I would call it, the general concern. I'm going to go to, okay, insanely gigantic. I'm going to start taking questions in the chat and Patreon questions soon. So if you have questions, you can start putting them in the chat. I have it on slow mode, so I need to get my Patreon thing up and running. But artificial general intelligence is a big concern a lot of people have. That artificial and general intelligence is going to destroy humanity, and people are afraid of that. So Elon, has always expressed concerns about that, and that's one of the reasons for Neuralink. But that's not necessarily a concern he has right now. So I'm going to do Patreon questions first. So if you're in the chat, you can ask questions now, but I might not get to them right away. I want to do these Patreon questions first. I will say, as I always do. Thanks to the Vasa Law Firm in Sweden, all my Patreon supporters, there's links in the description below. Patreon supporters get early access to some videos, they get bonus content, and they get to submit questions for live streams like this one, and there will be a Sunday live stream for those who are wondering. So Mark is a very consistent questioner on Patreon. He says, how much will development of a humanoid robot require? How long will it take to develop a humanoid robot? So, Elon said they expect to have a prototype robot next year, and I would guess that they will not have production robot until the end of 2023. We'll see. Mark asked, Dojo was to have been operational in 2021. Will it be operational in 2022? I don't know where you got that it was to be operational in 2021. It seems to me they are on a path to getting Dojo operational, I would say, in the next 6 months. Sounds like. I don't remember if they gave a date in the presentation. I think they hinted at, what progress they were making. I think they're in production, and then they've still got some hardware decisions to make and other challenges to get through. Mark asked, will hardware 4 be a free upgrade in every FSD car? I think if you paid for FSD, the answer is probably yes, but I'm not 100% sure of that. It may be that because it's not necessary to make full self-driving work, that it would not be a free upgrade in every FSD car. My guess would be that they might make it a free upgrade on all FSD cars that are bought after it's clear that they've announced it. So, and maybe if you're buying a Cybertruck, I don't know. Mark says, Tesla AI team has FSD in the bag. Do I agree? I don't think they quite... I'm very confident they're going to get there, but in the bag is probably too high level of confidence. You never know when they're going to discover that they're at another local maximum. That's the problem with that thinking. Eric asks, hardware 4 will be introduced in Cybertruck. Does that mean Cybertruck's at least another year out? No, not another year. Well, I mean, it sounded like it, yes. But, a year, right now we weren't expecting until maybe somewhere between January and March, and I think this pushes it to August. So that's like a 6-month delay, not a year delay, from where it is now. So yeah, I mean, that is a concern. I'm not happy about that because I have a Cybertruck on order and I want my Cybertruck. I have a Plaid Model X on order. It looks like I'll be buying the Plaid Model X and selling it when I get the Cybertruck. We'll see. Eric asked a couple of questions from audience on TeslaBot show they missed the first principle thinking at Tesla. One question was suggesting the humanoid could never look like that because of all the cables, etc. I don't know if I heard that question. I don't remember this question. One question was suggesting the humanoid could never look like that because of all the cables, etc. that would add weight and bulk. The other one about pricing. The questions largely got ignored. How would you have answered those? I don't think there's any question that Tesla can manufacture very well. I doubt that there's any issue with manufacturing it the way they want to manufacture. Will it be a challenge? Will it take longer than some people would like? Maybe, but I think, they've got a pretty good idea how to build things. That shouldn't be a problem. I don't see them adding weight. Delete parts, delete processes, you'll get there. And pricing, Yeah, Elon didn't give a straight answer, but I thought the point, if they're manufacturing at scale, I just think the point is, it should be relatively inexpensive. It should be less expensive than a car because it has less mass than a car. And if you think about the first principles, like you said, first principles thinking, if it weighs, if it has 1/30th the mass of a car, and it has, 1/30th the parts of a car, maybe it'll have 1/10 the parts of a car. It should be between 1/30th and 1/10 the price of a car. So if a car costs, let's say $40,000, then it should cost somewhere between 4,000. I could totally see them getting the cost down well below $5,000. We'll see. But, he's not going to answer that question yet. Ale or Ali says, for the first time ever, Tesla exceeded the expectation. They exceeded my expectation in some ways, not in all ways. I thought they were going to present hardware for, and they didn't present hardware for. So I think, Wall Street probably didn't understand it. The average consumer probably didn't understand it. Most people are taken away from this, they're going to make a robot. I think very few people got a full grasp of what Dojo is and why Dojo matters. And that simulation, what they're doing with simulation, I think very few people grasp how important that is. So the question is, considering how dirty all the Tesla Q are playing right now, they're going to utilize the fear that normal people might have after the TeslaBot presentation. What can Tesla do to avoid or mitigate that? I think Elon addressed that in the presentation. It's going to be slower than human. It's going to be weaker than human. It's going to be smaller than human. And if you watch Lex Friedman's interview with Jeff Hawkins, it's not going to have the intent. People have this fear that the robot's all of a sudden going to decide to be evil. It's not baked in. That's not where evil comes from. Mark says, still in shock over implications of a TeslaBot, transforms Tesla, robotics juggernaut. I think, how many trillions? He's asking how many trillions could a TeslaBot be worth in 5 years. I have not gotten to the point of trying to model how TeslaBot would affect the bottom line. I actually think that TeslaBot is an interesting development and potentially very important, but I can't wrap my head around it. And I think Robotaxi, is it bigger than Robotaxi? I can't answer that yet. Mark asked if I saw Bicentennial Man. No. Paul Payne says it looks like FSD won't be ready for several years. Paul, I don't know where you got that. My take from listening to Karpathy and Ashok and Elon, I think FSD better than human is going to be ready in months. And then, maybe a year. But, the hardware 4 chipsets coming out in about a year, and then that will take it to much, much better than human. So I think we're still potentially looking at robotaxis by the end of 2022. We'll see. Okay, so that's the Patreon Q&A. Let me go to our chat here. Let's have some fun talking. Oh, way over 3 hours here. So, Mark asks, FSD semi equals Goliath. I don't know what you're comparing. Maybe that's related to something somebody asked. I don't know what you mean, Mark. Will TeslaBot build a Mars colony? This is a very popular thing I've heard people say, is that, you're doing boring, repetitive work and dangerous work. Definitely Mars would be dangerous. I don't know that work on Mars would be boring and repetitive. So I could see that you would bring TeslaBots to Mars to do some of the work, because if there's any work that it can do that is dangerous work, you would rather have TeslaBot do it. And of course, TeslaBot can go out and do work on the Martian surface without having to breathe. So TeslaBot has a big advantage on the Martian surface over humans in that sense. Do I think Tesla will sell the TeslaBot, or do you think it'll be kind of like a robotaxi thing? Produce them and add them to the Tesla robot fleet? It definitely sounded to me like it would be for sale. I don't think it has. The robotaxi is a generic use. I want to go from point A to point B. I need a car to come get me and take me from point A to point B. The potential for TeslaBot is much broader use. It can do a lot of broad use cases that are undefined yet. And so I think that is an open question. What are the use cases? And so I think it would be sold. What do I think about TeslaBot mining for battery resources? I don't know that mining involves human labor as much as people might think. When does Tesla Yacht happen for shareholders? I don't know about Tesla Yacht. Is it just me, or was that TeslaBot hot? Gavin asks. So what I would say about TeslaBot was the important distinction is it did not look scary. It did not look big. It did not look strong. It did not look aggressive. It looked It's 5'8", 125 pounds, so it's smaller. I'm 6 foot tall, right? I almost wonder if they should have gone 5'6" or 5 feet tall to make it a little less threatening to small humans. But it's slow, it's weak, it's not. It has a non-threatening posture. I think overall, TeslaBot was well designed to minimize fear. Let's see. The robot uses 4680s. It will need to go on a diet. I disagree. I think 4680s may be particularly good for TeslaBot because because 4680 is the highest energy density. So it is an interesting question. What's the battery platform? What batteries would you use for it? If you want it to be lighter weight, then you would want it to use 4680s because that's going to be the lightest weight for the most energy. Lithium iron phosphate would be less expensive, but would be heavier. Ben says, what happens if you take your F-150 lightning to the supercharger, but now auto charge and discharge? I'm not worried about the F-150 lightning. I think that's too far off topic. Is it better than human? It's better than human in the ability to do repetitive tasks and boring tasks without getting bored. Will TeslaBot build a Mars? I think we already covered that. Let's see. Looking for questions here. What will low-end Optimus cost? I think we're talking about under $5,000, but we'll see. I think long run, once they manufacture at scale, I think this is one of the things, like, if they're going to make 1.5 million Model Ys a year, this is smaller and simpler. So why wouldn't they be able to make 15 million TeslaBots a year or 150 million TeslaBots a year? And the more they build them, the higher volume they build them, the less they cost per unit. Let's. Yeah, there is no volunteer list for Neuralink, but I do want a Neuralink, but not yet. I want it to work first. So I think they will have enough prototypes to send a couple of them to Mars in the next launch window. No, I don't think that they will be. I mean, maybe they would send a TeslaBot to Mars if they. They're not going to launch to Mars in 2022. In 2024, yeah, they should have some TeslaBots ready to go to Mars. I think that's when it would potentially happen. Suppose batteries will go in the feet to help them not tip over. I don't think that's an issue. I think the batteries will be in the torso, but who knows? That's a good question. I think that would mean unnecessary wiring. I don't know how they're going to do that. You think a person's view of economics colors their view of AGI? Is their view of economics in the limit? Thaddeus, that's too big of a question. I'm going to ask you, Thaddeus, to send me an email explaining that question because that's too big for my monkey brain. At least at this point. We crash into a crowd of humans instead of a wall because it's safer. Chris, I don't know where you're getting that. I don't think that's the way it's working. And I think people have this image that the car is going to make this decision whether to crash into people or shrubbery, in a split second. The reality is humans don't make good split-second decisions. The car is going to see the problem sooner than the human and make a better decision than a human before it has to make a decision. R.L. Copeland says, apply machine learning for the human brain with Neuralink. I definitely think that is something that's going to happen. Check my channel. I went through Siobhan Zillis's video where she presented about Neuralink, and I think that's something that she was saying, that she could see it going meta and using neural networks on neural networks. Active799 asks, Warren, do you see TeslaBot being the end delivery use for robotaxi? Not necessarily. I think if you listen to James Dauma, he thinks that maybe the bot would do the deliveries itself. Maybe the bot would ride a skateboard and do deliveries, or put a bot on roller skates. Why would you move a 4,000-pound car to make a delivery when you can move a 125-pound robot? VTR says, when will Dojo scale? I'm not sure that Dojo is going to scale. I think they're going to achieve the 10 cabinets of Dojo and start running, and then whether they're going to make a second Dojo or, I think that developing the next generation Dojo is going to take a while. So I would think that once they build the first Dojo, they'll probably build a few more. It partly depends on whether they're satisfied with it. Maybe it's not going to work as good as we hope. Will the TeslaBot charge directly from the car or a standard wall outlet? I would think it would charge out of a standard wall outlet. I don't know why it would charge from a car. I don't think that's a down the road question. It's an interesting question. Elon tweeted it's a quintillion floating point operations per second, enough to simulate a human brain. Speculation if he's hinting at something. No, he's not. How wrong will Wall Street take the AI Day news? As far as I can see, they haven't. When I looked in the morning, it was up 2%, so it seemed like it was okay. But I don't really worry about short term how Wall Street views things. I worry about long term what this means for the company. Cybertruck pulls up with 5 TeslaBots in the back, and they hop out and start building solar roof. I really think roofing robots, using TeslaBot to install roofs makes a lot of sense. I don't know if that's a big part of the cost problem with Tesla Solar Roof. I think a big part of the problem with Tesla Solar Roof is that the design of the roofs makes it difficult. So I don't know how much of the problem that solves. Total addressable market for TeslaBot is insanely large, Joanne asks. Will I be doing a revised share price model with this in mind? Not yet. I don't think we know enough about TeslaBot to come up with a valuation. I think we're going to have to figure out how much is it going to cost to make TeslaBot. Look, if TeslaBot is able to replace a human laborer, and that human laborer cost their employer $40,000 a year, or the cost of paying the wages, the cost of paying insurance, the cost of providing infrastructure that the human needs that a robot might not need. If the robot costs $10,000 and it replaces a $40,000 worker, or it replaces the work of, one robot replaces the work of some part of the work of a $40,000 worker, maybe that worker still does some other tasks, but you're able to hire fewer of the $40,000 workers, and you replace them with the robots, and the robots work 24/7 or 18 hours a day or something like that. The market's like insanely huge. I think you come down to this question of how much does it cost and how capable is it? And when you recognize this is generation 1 of TeslaBot and generation 2 will be more capable, the potential is really, really big. And this is where Elon gets to, you're wiping out a lot of labor, and the economy will have to shift to having this work done at lower cost means that the employer makes more money or the product gets sold for less money, and there's surplus. There's either producer surplus in selling the product or consumer surplus in buying the product, and consumers capture some of the surplus, and now consumers have more money to spend, so there's more to spend on other things that humans can do, like make YouTube videos. Sounds like a lot of military applications for Dojo. Do you think governments will steal the Dojo technology? No, I don't think governments would know what to do with Dojo technology. I don't see military applications for Dojo. I don't know where you get that. Maybe there's military applications for TeslaBot if you design it right, but the current TeslaBot is not designed that way. Will robots get rights SP so people don't sexually abuse them? No, the robots are not conscious. The robots are not thinking. They're not sentient. They are task-driven. Rob Markovich, why can't they launch Dojo now? Because they haven't built enough of it yet. They're still working on I think they need to make more chips, they need to make more tiles, and they need to make the cabinets, and they need to engineer the cabinets. They still have to have some challenges in engineering for the cabinets. BTR, thank you for your support. Bob Kebab says, that's a nice name, Bob Kebab. Bob Kebab says, Elon said we're all going to be on UBI, Universal Basic Income. The future doesn't look so bright when he talks like that. Well, if you read the Culture series novels by Ian Banks, that's one of Elon's favorite series of novels, and you can see some of the things you see in the Culture series in what Elon's companies do, like Neuralink. If we're getting UBI, we're able to enjoy life without having to work. I don't think that that's what humans ultimately need. I think humans ultimately, for me, humans need work. They need to do something meaningful, and just partying and drinking and having sex or whatever does not generate real meaning in life, and we need to do something. And I think Elon is a perfect example of that. Elon had all the money in the world. He could have just sat on the back of the yacht sipping drinks, doing coke and hookers, and instead he decided to do something meaningful. And I think Elon underestimates humans' ability to find meaning and to find meaningful work. Does Dojo have scaling issues fundamentally, as pointed out by someone in the audience? No, they answered that very clearly, that Dojo does not have scaling issues at all. And thank you for your support, VTR. No, Dojo does not have scaling issues. It's designed so that it's infinitely scalable, basically. Will the bots vacuum the house using a Dyson, or will Elon build a vacuum cleaner? I would think that you could train the Tesla bot to vacuum the house. Active 789. Warren, Elon said he believes in a universal income when robots get going. Thoughts? Biden giving money away in the future will be tough. Again, same thing. I think that humans need more than money. We need meaning. We need to do something purposeful. I feel that myself. I need meaning. I need to do something that matters. I don't just sit on the couch and watch Netflix and be entertained. I get tired of that. I need to do something. I mean, maybe you can find meaning in other ways. My friend Brian races electric motorcycles or electric bikes. How would Tesla create a robot by next year when it took Boston Dynamics long years of research? I think they have great engineering, and you know, next year's a prototype, but next year's not the actual product. Manufacturing is the hard part. Are the German unions going to go nuts? This is not designed to work in the factories. That's not what it's for. Will the bots pay union dues? A lot of union haters here, and I'm not a fan myself, but glorified test dummy. I think it's not that the first generation Tesla bot will be that useful. It's that it will learn, and it will Dojo and simulations and everything, it will be trained, and it will get better over time to be able to do tasks we need it to do. 3.5 hours. My God. Tom in the audience? Tom Nash. Hey, Tom. If you want to know Tom Nash, check out Tom Nash's channel on YouTube. Tom also talks about tech issues, and he's a good guy to watch. VTR, they did not mention issues with Dojo scaling. That is not correct. They mentioned that they still have engineering challenges to make Dojo work, but there was a direct question about scaling it up, and the design of the tile is that it resolves power and it resolves heating, and that the question about scaling was how they would deal with those power and heating issues as they scale, and they said they've got that built at the tile level and they can scale up. That's how I heard it, VTR. I mean, if you heard something different, find me the clip and send it to me. Tom says, look up Dan Ariely's research about Lego building and how humans are willing to take less compensation for a job with more meaning. Absolutely. I think that people are willing to work at Tesla and SpaceX and Neuralink for less money because they believe the job is more meaningful. I am personally, I'm an attorney. I could be making more money if I was motivated to go out and work as an attorney, and you know, I had a law firm, and ultimately I felt that my work was not that meaningful. Honestly, I mean, I did help some people, but ultimately I don't think I found that work that meaningful. And I came down to Florida and I tried to do a bunch of different things, and I have been searching for meaningful work for a while. And right now it's YouTube, and I'm really enjoying the YouTubing. I really enjoy the interaction with people like we're doing in the chat. But I crave more. So I've decided, you know, I'm on the path. Actually, tonight I'm going to be meeting with my my engineer about the design of the single passenger pod car robotaxi, and I want to see if I can build a single passenger pod car robotaxi. And I've got a path. Okay, this is what we're going to do. Sort of a rough idea of what we're going to do, and that's gonna, if I can build a vehicle that is going to provide low-cost transportation to the world's poor and accelerate the transition to sustainable energy for the world's poor, that has meaning. That's value. That's something important, and that's something I think we can do. Does Tesla have an ethics team? Anyone focused on how TeslaBot should interact with humans ethically? I don't think, well, first of all, TeslaBot is a long way from that point. I think ethics is an overstated issue. It's real. It's something to worry about, but I don't think, and I think the design of TeslaBot itself being smaller, lighter, weaker, slower, addresses a lot of those ethics issues right off the bat. I mean, I suppose you tell your TeslaBot to go steal something from down the street. That's an ethics issue. Is TeslaBot going to be capable of recognizing it's not supposed to steal? You know, maybe in later iterations they'll come up with that, but I don't think that's going to be coded in at the beginning. John Yent, so you think Tesla will solve FSD with current tech and improve it fast after Dojo is ready? I think that they will solve FSD with current tech. I think there's a question about whether Dojo comes online before FSD is fully solved. Really wasn't clear how fast, I don't remember it being clear how fast Dojo is going to be fully implemented. And I don't know the answer to that question. Thank you, Tom, for your offer of investment. The plan, Tom, just so you know, is that I am going to self-fund my single-passenger robo-taxi for at least the next year. At some point, I anticipate doing a crowdfunding round, maybe. And there is thanks to Emmett Thompson from Clubhouse, I learned about the Advanced Vehicle Technology Manufacturing Program, which I should be able to borrow money for. The beautiful idea, I want to create a small EV company. The EV will be small, the company will be small. At some point, I think the biggest challenge is going to be finding self-driving software and hardware when it's ready, when the vehicle's ready to go, which is probably a few years away, and then finding markets for it, because my design for the self-driving single-passenger podcar robotaxi is it's not designed for U.S. roads, which are too dangerous for this vehicle. It is probably designed for third-world countries where it's better than the crap they're driving around in now, and maybe for boring company tunnels. So I'm not sure how big the volume will be initially. And then if we get to the point where we need to scale up manufacturing, then we will look for a larger investment. But I'm hoping that the early rounds generate enough capital that it can feed itself and grow itself. And the technology is not going to be that innovative that somebody won't be able to come up with something similar. It's not, I don't have some brilliant idea for some fantastic new tech. It's just optimizing a vehicle for a single passenger, maybe 2 passengers because of the advanced vehicle technology manufacturing thing, whatever. Optimizing it for that so that we can lower the cost of manufacturing, lower the cost of, make it more efficient, reduce weight, so on and so forth. Ken says, Elon implied that today's FSD hardware is sufficient for robotaxi. If hardware 4 is required for robotaxi, will we need a class action suit to get Tesla to do the right thing, or will the upgrade be free? So I'm not a class action lawyer, and I would not sue Tesla, and I think that's, personally, I think that's a silly question. They're trying to do it. There's no class action suit. They never promised you. There's no, like, we're going to deliver it. You paid a low price for early access to the prospect that you would get something much more valuable later. And if you don't understand that, then you didn't understand it. Jason Carpenter, your podcar sounds good. Remember the film Sleeper? I remember the film Sleeper, but I don't remember the car. I vaguely remember the car. I'm going to have to go look that up now. Steel Curtain says, I know an attorney's been practicing law in excess of 20 years and they're leaving it for the same reason. I've been an attorney for 25 years. Sorry, dog wants out. My dog is tired of the live stream. So, yeah, I mean, I think, I think that's one of the things that, like, it's not that being a lawyer was not meaningful work. I really helped a lot of people, especially in I really feel like in my criminal cases, I represent a lot of people who are charged with crimes who had underlying mental health problems. And I helped a lot of people get the right mental health help, which I was able to use that to get them a better result on their case in terms of plea bargaining. But I also was able to get them the mental health help that helped them to not have these same problems again. So for me, that part of the work was very meaningful. But I don't know. Overall, the work is a drag. And, I think work in general is a drag. So, sorry. Jeannie Gogo says, Warren, your current work is really good and meaningful doing this. No, I agree. This is meaningful. It's not that I don't plan to stop doing the YouTubing. I just plan to, in addition, do the single passenger EV. And if the single passenger EV goes well enough, then at some point, maybe I would have to stop YouTubing, but that's a way down the road. Active789 says, Warren, would you take a home equity loan on your house to buy more Tesla shares? We will look back and kill ourselves if not. I would, but my wife would not. I have actually had that conversation with my wife, and my wife has said no. And she's probably making a good judgment. I own enough Tesla stock that if Tesla stock goes where I think it's going to go, then I'm not going to be a billionaire, but I'll be wealthy enough that all this stuff becomes trivial. There's sort of this question like, how much do you need? Let me just talk about this really quick for a second. How much do you need? So, like, I would like to have more money so I can build more companies, right? But in terms of living, I lived in a 200 square foot apartment in Hiroshima and I was happy. I live in a 3,200 square foot house right now and I'm happy. If I had 10 times as much money, I suppose I could buy a 10 times bigger house. Would I be happier? I don't feel that I need to have a lot of stuff. I don't think the money buys me stuff that makes me happy. I don't go out and buy stuff. I don't go buy fancy clothes. Look, insanely gigantic. I think this is like $25 for you guys. And of course I get a discount. I get it for like $15. But, buying t-shirts, buying stainless, this stuff is all easy for me to afford now because I have that much. But I don't want to buy a yacht. I don't want to buy a private jet. I don't need to buy a private island. I'm happy with my life as it is. So the additional money, if I end up with 10 billion or I end up with 50 billion, if I end up with 10 million or I end up with 50 million, how meaningful is that difference? And I'll put it in this context. Suppose you accumulate a certain amount of money and you're done, you're not working anymore, you got to live off this money. My attitude is that if you take 5% of your pile, right, you've got a pile of assets and you take 5% of the year and you spend it, and that's what you live on, and your pile grows 5% a year, then you're at steady state and you're good. And you'll never run out. So if you have $1 million, that means $50,000 a year, 5%. If you have $2 million, it means $100,000 a year. If you have $5 million, it's $250,000 a year. If you have $10 million, it's $500,000 a year. I fully expect that the amount of Tesla stock I have and where I think Tesla's going to go, I'm going to have more than $10 million in net worth when this is all done. So that would mean I would be able to spend $500,000 a year. I don't know how to spend $500,000 a year. I don't know what I would do. What other than investing it and building another business, right? I don't need a $500,000 car. I don't need a $10 million house. I don't want to need a yacht. I don't have the desire. I don't need to take long vacations and expensive vacations. Whatever people are spending that money on, I don't need it. So, and that money will go to my kids, and my kids will, if I don't spend it, then my kids will have more because it will grow. So I think that's the challenge there. So, it's not worth, getting in a fight with my wife over the home equity line of credit. Let's put it that way. Let's see. Why buy a Tesla when I could just buy a bot to drive me around? That's an interesting thought. You buy a bot to drive, I buy a bot to drive, but the Tesla's a better car overall anyway. You don't have to buy FSD. You buy a Tesla without FSD and you buy a $5,000 bot to drive the car. I like the thinking, but I don't think it works. I don't think the bot's going to have as many cameras. Well, the necessary safety equipment will drive up the cost in your single car. The car is not going to be operated on U.S. roads, so it won't need the safety equipment you're thinking of. Do I think the proposed bot still fits in with your idea of installing solar roofs? I think the bot would be helpful with solar roof install. I think there's a lot of work that goes into installing solar roof, but I think ultimately the reason that solar roof is costing more is because of some other complexities that the bots would not be good at. So it may reduce the cost of solar roof, but it doesn't fix the underlying problem. So I think the single car will be safe. I think the single car will be safer than motorcycles and bicycles and pedestrians if it's hit by a car, and it will be safer driving than a human driver, but it will not be as safe as a Tesla Model 3 or even my Volkswagen Passat. And people keep telling me to look into Arcimoto. Oh my God. I get this all the time. Warren, you should look at Arcimoto. Warren, you should look at this other single passenger car. Warren, you should look at Aptera. Arcimoto is $18,000. At the beginning, it starts at $18,000 and their dreams are going to get down to $12,000. Aptera is $25,000 minimum. I want to build a car that costs $2,000. Okay? You can build a car that costs $18,000. Look, my Volkswagen Passat cost $18,000 and it seats 5 people and it'll go over 100 miles an hour and it has 700 miles of range at 75 miles an hour on the highway. Arcimoto sucks compared to that. You want something that's better for the money. And I think Arcimoto is good in a very narrow context, but it's not what I'm looking for. And it's too expensive, and I don't think it has the durability either. It's got to last hundreds of thousands of miles. What will you use instead of Dojo for training your pod car? Andy, the plan is to find others who have produced self-driving hardware and software to do the navigation. I think the other interesting question is, what will I do? I'm anticipating it being used for fleets. So will the fleet use the Tesla robotaxi network, or will we need to develop our own network? Maybe after Lyft and Uber go bankrupt, we'll buy one of them and use their networking software, software to be able to let people summon rides. Do I think the TeslaBot will have a replaceable battery so it can change its own battery? I think it will have a battery that lasts a very long time, but I do think it would probably be I think that's an interesting question. I think that probably the battery will outlast the bot. Oh, Tom, that would be great. Yes, please send me an email. I'd love to come on your channel. Big fan. A VTR, I'm not sure what you asked. You can't build a $2,000 car without being a puppet to Chinese manufacturing. So VTR, you're probably, I don't like your language. I think there's a tremendous amount of hatred for China that I see in YouTube comments and I see on Twitter. And I'm not saying I'm a fan of the Chinese Communist Party, but the practical reality is the Chinese government has been more favorable to Tesla than the California government or the German government. So this notion that China is somehow evil and unfair to Tesla, or, and I'm not saying like, do I think that there's evil in the Chinese government? Sure, there's evil in the US government too. I think the US government is much more dangerous than the Chinese government. I think that Chinese manufacturing is really, really good. I think my design for my rough design in my head for the single passenger pod car, I do think we can do it for less than $2,000 in America. Absolutely. The key is, can you look? Tesla is building cars. It's going to be building cars in Texas very, very cost effectively. It is possible to manufacture cost effectively in the United States. You have to design it to be manufactured well, and you have to design it like, just really, for example, just to give away one thing, I'm going to use standard 13-inch wheels, right? Standard 13-inch wheels, standard 13-inch tires, 155 80R, 155 80R13, I think, or 155 75R13. Standard tires that you know, you buy those from the manufacturer, and standard 13-inch wheels, buy those in volume from the manufacturer, you get a really good price on them, and they'll last forever. The tires will last forever because they're designed to carry 3,000 pounds, and my car's going to weigh 1,000 pounds. So VTR, if you want to email me and say this is VTR from the chat, and you want to have VTR, I really appreciate your support. I understand your question is common. I don't agree with your question, your premise. But if you send me an email and say, hey, Warren, this is VTR from the chat, I want to talk to you about China. You know, given that you've supported me in the chat, I really appreciate that. I'd be happy. I don't normally engage with people that much in emails, but if you tell me your name and that we talked about this, then I will engage with you. I just don't want to continue that conversation in the chat. What are the implications, monetization opportunities of such a broad and detailed simulation in the real world paired with real-time sensor data, updating that simulation continuously? Well, there's some really, really big implications to that if you want to get into whether we're in a simulation right now and we don't realize it. If we can create a completely realistic simulation and we can create non-player characters that are operating in that simulation that don't realize they're in a simulation, then how do we know that somebody else didn't create the simulation that we're in now? There's a t-shirt on my, Insanely Gigantic is one of the t-shirts. One of my new t-shirts on elonbits.com is the non-player character shirt, which isn't selling well, so don't bother. There must be, you want to have a unique one, there must be other cheap sweatshops in the world besides China. Wouldn't India embrace pod car production with open arms? I don't think this is about sweatshops. I don't think that what I want to do is it true that Grimes was the dancing bot? I suspected that. Wouldn't India embrace? I think that pod car production will happen. I honestly think, I don't expect to have a monopoly. I don't expect to have a monopoly on single passenger vehicles. If I'm right and it takes off, then other people will be able to copy it. It won't be that hard to copy. China is making like $1,000 cars that are 4-passenger vehicles. So I don't think it's going to be that hard to copy the concept. It's, you know, I think mine will be optimized better and will end up with a lower cost per mile because of the design. But other people will make something similar that will be roughly competitive. Do I still have an interview with James with his take on I do expect James Dowma to interview with me. I think it's the 22nd. I'm not 100% sure. Oh, do margin? Yeah, okay. I'm not doing that. I do have margin authorized on my accounts, but I don't use it. Any hope for Giga Schenectady? No. Somebody asked me about Giga Osaka in Japanese, and I actually was able to read that. And I go faster to catch up. I don't know what you mean. Did Tesla announce a robot yesterday? Is this a dream? That was real. I think I genuinely believe that TeslaBot was a distraction. It was something to give the masses so they would understand something out of what happened, because there's no way most of the Wall Streeters and the journalists understood what Dojo was. Dojo was like monster. If you didn't get Dojo, wow. I mean, Ganesh's presentation about what they're doing with Dojo was absolutely mind-blowing. The space that it takes up, that it uses less energy, the flops, the application, as Elon described it, it's an ASIC for neural nets, for neural net training. That is a nuclear bomb into the future of AI, a positive nuclear bomb to the future of AI. We're going to see radical increase in machine learning ability. What do I think Tesla will be worth in 5 years? Well, my current projection for Tesla in 5 years is $25,000 a share. I don't feel like I know enough to adjust it. I would say this. We know we're adding a business line for AI training. We know it seems like we're adding a business line for simulation, providing simulation services. Simulation as a service, Dojo as a service, and we're adding TeslaBot. It's got to go up. So anyone calculated how many shares of Tesla Warren has? I have between, right, I tell people I have between 50 and 5,000 shares. I have between 50 and 5,000 shares. I don't think I've ever given enough information that anybody could calculate how much I have. But I have a lot more than 50 shares and a lot less than 5,000 shares, to say that. Yeah. And it's with the shares that I have and shares that I control on behalf of my mother. For those who follow my story, I'm moving my mother to assisted living on Monday, to a different assisted living. Any predictions on what revenue TeslaBot could produce? So let's go with let's play with this. Let's suppose a TeslaBot costs $10,000, and let's suppose they can make $10 million a year. I think that's $100 billion a year in revenue. I don't see why they couldn't make. I definitely think it would be worth $10,000 if it's able to replace the labor of a $40,000. If it's able to replace half the work that a $40,000 a year worker does. And let's not forget, it's able to work 18 hours a day instead of 8 hours a day. It's easily worth $10,000 to the buyer. You know, you're going to have to work around it. You're going to figure out what tasks can it do and what else does the other workers do? How does it work with humans? How do you integrate it into your job? But it really seems to me straightforward that you could sell it for $10,000. I think they might be able to sell it for less, but let's suppose it's $10,000. Nice round number. And if they can make 1.5 million Model Ys a year, there's no reason they couldn't make 10 million TeslaBots a year in the long run, not immediately, but 5-10 years down the road. That's $100 billion a year in revenue. If it costs them $5,000 to make it and they sell it for $10,000, then there's $5,000 in margin, $50 billion a year in profit, price earnings ratio of 50.5 trillion, 2.5 trillion in market cap, $2,500 market share price just on that. I own. I don't like to say how many shares I own. I own. Why the secrecy regarding the shares? I just think that's private information. It's not just mine. It's it's families. It's not just, if I was an individual, maybe I wouldn't care, but it's on behalf of a family. So I think it's not appropriate for me to talk about it. Not as much as most people think. It's still a lot. I'm not worried about my financial future. For training TeslaBot, what's the source of data? Oh, for training TeslaBot, what's the source of data? So initially, it's like they actually mentioned using simulation for TeslaBot, but you get the first TeslaBots out there, and they walk around the world, and they use probably the training from the cars and training from simulation. Start with simulation, and they just go out there and move around, and you start generating more. But I think you have the baseline of what you know about the real world from the cars. I should say my mother has more Tesla than I do. ETR, Dojo is just like 1,000 cores on a board. The real breakthrough is when you can do the same test with 50 cores. What do you think? First of all, thank you again for your support. 1,000 cores on a board, the real breakthrough. So, no, I think that if you can design, first of all, it is a very, very efficient chip. And I think the future, I don't know that I think, first of all, I think you're speaking over my head a little bit, VTR, but second of all, I think that might be incorrect. The history of computer chips is putting more and more transistors on a chip. And to some extent, I think they've gone to larger chip sizes. But the real breakthrough here was making the chips. Well, there was a breakthrough in terms of designing the chip itself, the node itself, which is on the chip, to be optimized for neural net training. And then designing the chip to have all the nodes and the scalability. Oh, what's Brian Smith say? Not should replace more than a $40,000 skilled laborers. Skilled labor technically works an 8-hour day. A bot could work multi-shifts. Yes, exactly. So the problem, Brian, and Brian is in the chat, is as a Patreon supporter and my neighbor and friend, and we've been texting because we talked about RVs and stuff. Brian is the one who rides electric motorcycles. Brian is I'll call you, I hope it's not inaccurate, Brian, a self-made man, a guy who's actually been in business and hired skilled laborers. So I think this is a question for you, Brian. What I see is that your skilled laborers, they do a lot of work that's routine, was repetitive, boring, and maybe dangerous. Some of the work that your workers do is stuff that the TeslaBot probably couldn't do. So if you have a worker who's getting $40,000 a year, not necessarily a paycheck, but they're costing the employer $40,000 a year, including Social Security and workers' comp and insurance or whatever you're spending. Let's suppose you got a $40,000 a year worker, and half of what they do is repetitive and boring and dangerous, or dangerous. And you can have TeslaBot do half their work, and you have 100 workers like that, and you can have TeslaBots replace some of those workers. So you reduce the number of workers by half or even 3/4. You still need the human workers to do something. The TeslaBot probably won't do everything they can do, but you may end up needing a lot fewer workers, and that saves the employer a lot of money. So if you were paying $40,000 for 100 workers, and you end up replacing 50 of the workers with TeslaBots that cost $10,000 a piece, that's a massive saving for the employer. And maybe you end up able to replace 80 of the workers with 20 of the TeslaBots, and your business ends up being much more efficient. You're able to earn more money, or you're able to charge less to your customer and make more money. A lot of really good things there. Oh my God, we're going on 4 hours here. Not quite at 4 hours because I started late, but we're heading close to 4 hours. Future is 3D printed solar roof. I don't think Elon doesn't like 3D printing. I think 3D printing, Elon has said 3D printing doesn't scale. Hooterman says $100,000 plus per TeslaBot. I think it depends on how much the TeslaBot can do, but ultimately depends on how much it costs to make it. If you produce it at scale and you're able to produce them in high volume, then either you're selling it for $100,000 and you're making insane profits on it, or you're selling it. I think if you want to sell them in higher volumes, you want to sell them for less money. And the real secret to TeslaBot is going to be producing it in high volumes. Will Dojo be an industry by itself? Yes. Well, not an industry by itself. Dojo will move it. There's an industry called AI training computing. AI training compute. Check out ARK Invest's 2021 Big Ideas white paper, and they talk about this as a growing industry, artificial intelligence, and Dojo will play a key role in AI training. Dojo as a service, once they get past FSD, once they solve FSD, that's the full focus now is going to be FSD and then TeslaBot FSD, or TeslaBot AI, TeslaBot Vision. At some point, I think you're going to get to multiple dojos that are doing different tasks. You can divide Dojo up and use different parts of Dojo for different tasks. And then you're going to have next generation Dojo. And is that going to be used for more FSD training, or is that going to be used for other tasks? There's a lot of neural net training to be done out there. When is Tesla price going to dip? I don't make short-term stock price predictions. I have no idea. I just that's not me. That's not the kind of guy I am. I just don't know. I think anybody who thinks they know doesn't really know. How does robot manufacturing fit the mission of Tesla to advance the adoption of sustainable energy? Great question, Tom Collins. That is a great question. I have to think on this one for a second. So, a human laborer uses a certain amount of energy. They use energy in their car to get to work. They use energy on the job to be warm or cool. If you are able to use a TeslaBot, I think that ultimately the TeslaBot will use less energy to accomplish the same mission that the human was doing. And ultimately, basically, if the TeslaBot costs less to do the job than the human, then something that costs less probably used less energy. I hope that explains it. The cost of freedom is measured in dollars. I don't know where you got that. I don't know who you're talking to. Why the secrecy regarding? Okay, so I've answered that. Did Elon say he will sell them or maybe rent them? I think that it's a sales model. I think that the rental model doesn't make necessarily. Maybe they'll do both. I think the majority of revenue from TeslaBots will be from after purchase software upgrades. That is an excellent point, Lee. It could very well be that you buy your TeslaBot and then they're like, hey, we've got a new round of the software that is, we've improved it. Or maybe it's a subscription model for the software, for the AI vision software and the training. Sex bots. I don't think it's designed as a sex bot. I'm not saying it can't be a sex bot, but I don't think it's designed for that. I don't think you would necessarily like that. VTR, thanks again for your support. Are there any significant competitors to Dojo right now? I don't think so. I think there are other AI training supercomputers out there. I don't think they're as good as Dojo, but Dojo isn't there yet. But as far as I know, no, nobody's got. I mean, there are other AI training. I think Google does AI training, but I don't think they're on the same level as where Dojo's heading. Do I think Singularity Net will be used at all in TeslaBot? I don't know what Singularity Net is, so I can't answer that question. Will the bots be regulated, 5 per company, for example? I don't think so. I don't know why you would regulate them in that way. Tesla uses electricity instead of food resources. The former will eventually become abundant. The latter will not. I think food is going to become abundant too. I think if you follow Beyond Meat, Impossible Foods, lab-based meat, I think food is going to become more. Food is already abundant, frankly. Here in America, we're all fat. I got a big belly on me. Does the TeslaBot change your opinion of universal basic income? No, the TeslaBot does not change my opinion of universal basic income. I think that people underestimate the ability of humans to find meaningful work, and getting a basic income does not give you meaning in life. You need to do something meaningful in order to have meaning in life. If you don't have meaning in life, then your life is meaningless, and that can be very frustrating. And I would encourage people to follow Jordan Peterson and watch some Jordan Peterson videos. He's got a book, 12 Rules for Life. I don't think you get meaning in life out of getting paid and then sitting on your couch and eating chips and watching Netflix. That's my opinion. You can have your own opinion. See. Will Tesla have better success selling their robots than Boston Dynamics? I don't even know if Boston Dynamics is selling their robots, but yes, absolutely. The Boston Dynamics robots are not AI. They're just machines that can do what they're told. Tesla bots will cost a lot less money. I think, was it Dogbot cost $75,000? Tesla bots will cost a lot less money, and they'll be able to do a lot more. They'll be a lot more capable. Will Tesla bots have infinite personalities? In the short run, I don't think they're going to have much personality at all. In the long run, I suppose personality could be something that be added, but I don't think that's really part of the design. Maybe Tesla bots will replace government officials. Well, I don't want to go there. Training bot. Because it is human-like, you must show it what to do. It uploads the video to Dojo. Dojo returns a program in a few seconds. Bot loads the program, and you're good to go. I don't know. I think it needs to train on understanding the world, not to understand a task. Maybe task training is going to be a separate thing. Tesla bots. A lot of people talking about Mars. I don't know what Singularity Net is, so I can't answer that question. All right, let's see. I think the bots would help the elderly and disabled. Yes, absolutely. My mother's in assisted living. My mother's moving to a different assisted living. I think that the task of caring for the elderly and disabled, some of the work really requires human touch and human caring, but some of the work, like cleaning up messes, the elderly tend to make messes, poop or pee or whatever. Having bots clean up messes would be a lot better than having humans having to do it. Boring, repetitive, or undesirable work, unpleasant work, and then that can leave the humans to do the caring part, the caring part that the bots probably won't be able to do. Do I believe the TeslaBot dances better than the Boston Dynamics bot? The TeslaBot does not dance yet. It's not even a prototype yet. I think Neil Evangelista, thank you for joining the channel, your support. Thanks for the chat. Really nice to see Neil Evangelista here. Neil is a friend of mine from Boca Raton. We got Brian Smith, my friend from right over the lake, and I think Neil's in East Boca. Unskilled labor gives meaning in life. Yes, unskilled labor does give meaning in life. Doing something meaningful gives meaning in life. I don't know about unskilled. I would say physical labor gives meaning in life. Can give meaning in life. I think that's a question. Where I can't tell you where to find meaning in life. I can tell you that sitting on the couch watching Netflix, generally speaking, look, I watch Netflix, right? What have I been watching? I've been watching this program, Utopia, a 2013 show on Amazon Prime. I've been watching. I don't really watch a lot of TV anymore. I watch some YouTube videos. I watch people like Tom Nash on YouTube and Dave Lee and Rob Maurer and stuff. But Lex Friedman. You think that? So I answered that. Did Elon say for how long he's been working on this bot idea? He did not. Sid123 says, Jordan Peterson, you lost a lot of respect, Warren. Well, Sid, I'm going to guess you haven't read the book. Why don't you read the book and then tell me? I read his book. I was really impressed by his book. I thought it was really insightful. So you can say that you have no respect for Jordan Peterson if you want to, but try reading the book. Don't just read what people say about him. Actually read his book, 12 Rules for Life. If you can read the book, 12 Rules for Life, and tell me that that is not a good book, then I want to hear why. Email me. Tell me you read the book and tell me why you think his book is a bad book. You can disagree with him about some other things, but read the book. Tell me what's wrong with the book. Absolutely brilliant. 12 Rules for Life, highly recommended. Recommend it for your kids. Can't get my kids to read it, of course, but will Tesla bots be deployed as pilots in the U.S. Air Force? No. That is not the design. That's not what it's for. Do you think that Tesla bots will allow custom faces displayed on their screen? Probably. I could see that coming. What is the pay range for recent AI graduates? I think AI software engineers are making easily six figures and easily low six figures and probably $200,000-$300,000 a year at Tesla. If you become if you rise at a company like Tesla and you're doing AI software engineering, you're probably making $200,000-$300,000 a year or more. And then I think there are companies that pay more. I think Tesla gets away with paying less because it's such a good place to work. So yeah, Night Trekker says, Jordan Peterson points out there's a large part of the IQ bell curve is below 80. Most people can only do manual labor and are not trainable. So this is where I disagree with Jordan Peterson. He's probably right. I'm not saying he's not right. I think that people can always find meaning. They can always find something to do that has meaning, even if it's unpaid. Sid123, I will read that if you read Mein Kampf. What makes you think I haven't read Mein Kampf? But just to be clear, Mein Kampf is a really boring book. I tried to read it. It was absolutely boring and stupid. I am telling you that Jordan Peterson's book is absolutely brilliant and not stupid and an easy read. It's not translated from German, which makes it even harder. It's harder to read books that are translated from other languages sometimes. Would the bots be able to play games with human owners? Probably. I would think that playing games would be a useful thing for it to do. Sometimes playing games with children, for example, can be really repetitive and boring, or playing games with dogs. You could see a bot being something that could play with a dog. Be an interesting question. Would a dog play with a bot? Would a dog play with a Tesla bot if the Tesla bot was trained to play with a dog? Or would the dog just not be interested? That's an interesting question. So anyway, back to Neil Evangelista. Yes, I think roofing bot is definitely a possibility. All right, so is FSD learning an AI environment a novel idea? I think so. I mean, it's not novel now. My high school teachers were mostly below IQ 80 and it didn't stop them from teaching. Very funny, Jim. I would say that in general, my teachers have been very bright. And did I have an occasional teacher that wasn't that bright? Maybe, but I don't think I had a teacher who had an IQ below 80. I don't think you understand IQ below 80 if you say that, Jim. A dog would most likely wee on a Tesla bot. And the Tesla bot wouldn't mind. All right, so we've gone over 4 hours, I think, or about 4 hours, and I think the questions have petered out, and I don't know how we're doing on number of people watching. Yeah, we're down a bit. So I think it's a good time to end it. I want to thank everybody for watching. My regular live stream will be on Sunday. Please check out the channel on Sunday. I'll probably talk about AI Day as well, and some additional learning from other things we learned about AI Day. Probably talk about Starship. Probably talk about other stuff. Thanks everybody for watching. This was a marathon session. Really appreciate everyone watching. Really appreciate the support in the chat revenue. Thank you to the moderators. Thank you to the channel members. Thank you to Patreon supporters. Thank you to the Vasa law firm in Sweden. I probably should be thanking somebody else, but thank everyone for watching.